predict its outcome. Also, if you use them for Monte Carlo simulations, they can actually give false simulation results. The obvious solution is to use a physical process as an entropy source for random number generation. One is particularly interested in stochastic and quantum processes like noise, radioactive decay, electronic jitter, or quantum fluctuations. This is an example where the phase fluctuations of a single mode laser induced by spontaneous emission noise are used for random number generation. So these fluctuations are used using a delayed self-homodyne method. The big advantage of these approaches is that they are intrinsically secure because they are based on the unpredictability of quantum mechanical processes. However, they are relatively slow. For example, this laser system here has a maximal bit rate of only 20 megabit per second, which is significantly too slow for most applications. Another source for physical source for entropy that has been discussed a lot are chaotic dynamics, in particular of semiconductor lasers. As you all know, they have a very fast dynamics, which can be exploited. A very simple and early example here is the use of a normal diode laser, which is rendered chaotic via optical feedback from an external cavity. And then the chaotic output of the laser is measured. Here you see an example of a time trace, which is then digitized and post-processed to generate random numbers. And with such approaches, bit rates as high as 2 terabit per second have been achieved. Nonetheless, these bit rates are limited by the chaos bandwidth of these semiconductor lasers, which in turn is limited by the intrinsic timescales of the semiconductor active medium. So if we want to further increase the random number generation rate, we need to use other tricks. And one approach would be to parallelize it. This brings us to the broad area laser. So our idea is to use a broad area laser to generate parallel bit streams via spatial multiplexing. And, well, first we need to take a closer look at the spatiotemporal dynamics to see if that works. In the following, I show you experiments with homemade broad area aluminum gallium arsenide quantum well lasers. The typical device is 1 millimeter long and 100 micron wide. They are pumped electrically with 1 microsecond long pulses at a low repetition rate to reduce heating. To measure the dynamics, we image the output facet of the laser onto the entrance slit of a streak camera. And the streak camera then measures spatiotemporal images where one axis corresponds to the position of the output facet and the other axis is the time. And we can achieve picosecond resolution with the streak camera. Here you see an example of the measured spatiotemporal dynamics. So the vertical axis here is the position on the output facet. The horizontal axis is the time in nanoseconds. And as you can see, this output pattern is very complex and unstable. First of all, you can see that the intensity is not homogeneously distributed over the output facet, but rather concentrated in certain hotspots, so-called filaments. And on top of that, these filaments pulsate irregularly, and you can also see strange diagonal patterns like here, which stem from filaments moving transversely in the cavity. The important consequence of that are long-range spatiotemporal correlations. Here you see the spatiotemporal correlation function as a function of time delay and spatial separation. And you can see that apart from the center at zero delay, there are also significant correlation with in space and also in time. And that is, of course, that is prohibitive for using them as a random number generator. An important part of the problem of why this filamentation appears is that Fabry-Perot broad area lasers lays in a number of different transverse modes. For a 100 micron wide device, you typically have 10 different transverse modes, as shown in this spatial-spectral measurement here. There are two issues with that. First, these are too few spatial degrees of freedom for a truly massive parallelization. And moreover, it is the interaction of these different transverse modes via the active medium that leads to this filamentation dynamics. So how can we get rid of it? There has been a lot of work invested in stabilizing these broad area lasers due to their importance in high power applications. Common approaches are optical injection from a master laser, filtered feedback from an external cavity, or the use of unstable cavities with a concave output mirror like the one shown here. And what these approaches have in common is that they aim at reducing the number of transverse modes, since in single transverse mode operation, the filaments will of course disappear. However, these solutions are not suitable for us because we need many transverse modes for parallel random bit generation via spatial multiplexing. Hence, we pursue the opposite approach to suppress the filamentation, and that is to vastly increase the number of transverse modes. This brings us to the stable cavity laser, which was designed with that goal in mind. So I'll introduce you how do we manage to increase the number of transverse modes and how that affects the spatial-temporal dynamics. So how can we increase the number of modes? If we look at the normal Fabry-Perot laser, the fundamental transverse modes correspond simply to ray trajectories bouncing back and forth between the mirrors. However, higher order transverse modes like the one shown here have a finite transverse component of the momentum vector. That means the underlying ray trajectories run out of the cavity laterally and get absorbed after a few round trips. And therefore, high order transverse modes have relatively high losses and cannot lace. The solution is quite simple. That is, we use two curved mirrors in a stable cavity configuration to periodically refocus the light in the cavity. And this way, even so you can see this at this example of a trajectory which always remains inside the cavity. And as a consequence, even high order transverse modes like the one shown here have quality factors that are good enough to permit them to lace. Now, in detail, we have to take a look at how to optimize this cavity geometry to have the most transverse modes possible. For this, we did simulations with a smaller cavity. So we considered a cavity 20 micron long and 14 micron wide. And then we varied the radius of curvature of the mirrors. So we parameterize this with the so-called stability parameter, G equal to 1 minus the length divided by the curvature radius. Here you see the results of COMSOL simulations coupled with SALT, so-called steady-state ab initio lasing theory, which allows us to take into account the spatial hole burning and mode competition effects in the laser. The graph here shows the number of transverse lasing modes as a function of the cavity stability parameter G. And for an operation of 2 or 3 times above the threshold, we find a maximum at G equal to minus 0.74, which is the so-called near concentric cavities. So we can here we find up to 25 modes, but when we increase the cavity to a few hundred micrometer, we should have several hundred transverse modes in effect. Here again, a sketch of the stable cavity laser. So the curved mirrors were etched using UV lithography and dry etching. The fabrication was done by our collaborators in Singapore. And the top contact was designed in this hourglass shape to align it with the profile of the high order transverse modes. Here you see the top view SEM image of a typical cavity, which is 400 micron long and 280 micron wide with a curvature radius of 230. Now, to test whether our design actually works, we did speckle contrast measurements to determine the spatial coherence of the laser. So the laser output is passed through a line diffuser, and the resulting speckle pattern in the far field is recorded with a camera. And here we obtain an extremely low speckle contrast from which we can estimate that we have up to 1,000 transverse modes lasing simultaneously in this laser. Let me remind you that for a Fabry-Perot laser of the same width, we would only have a few 10 transverse modes. Now, the very low spatial coherence of such a laser is not practical if you want to use it as a high power laser, for example, for machining applications where you need to tightly focus it. However, it is impossible to, however, this laser is also interesting for applications that require speckle-free imaging, for example, in full-field microscopy. But let's take a look at the spatiotemporal dynamics. As a reminder, let me show you a streak image measured with the maximal temporal resolution of a conventional Fabry-Pérot laser. Again, you see this filamentation dynamics and the spatiotemporal correlations associated with it. This is now the stable cavity laser. As you can see, these filaments have completely disappeared. And instead, we see a grainy, random, and seemingly uncorrelated emission pattern. So what happens is that once the filaments are gone, the only thing that we see here is the interference between the many longitudinal and transverse modes, which results in a spatiotemporal speckle pattern. And this is it's an intriguing example of how the cavity geometry can be used to change the spatiotemporal dynamics in a quite fundamental way with only a very simple change of the geometry. The time trace of one spatial channel, for example, here in the center, you can see that we have an irregular and aperiodic time trace, which is ideal for random number generation. Moreover, we see that the filamentation has completely disappeared. Here you see again the spatiotemporal autocorrelation function, and there are no longer any long-range correlations. So that is an important prerequisite for random number generation. So why are we able to suppress the filamentation in this device? So let us first go back to the conventional Fabry-Pérot laser. Since the transverse modes have relatively low order, the transverse wavelength is large. It's of the order of 5 to 10 micrometer or even larger. And when we have an intensity variation in the transverse direction on this length scale, this will locally deplete the gain via spatial hole burning. And since the carrier densities are gain, meaning the gain and the real part of the refractive index are coupled in the semiconductor medium, the refractive index is locally increased, which leads to an optical lensing effect, which leads to the formation of these self-organized filamentary structures. And these filaments are, however, intrinsically unstable because the lensing effect and the gain guiding effect counteract each other. So since the gain is larger to the left and to the right of the filament tries to move, or it runs out of gain and new filaments in other positions are formed instead. In our stable cavity laser, however, we also have very high order transverse modes with transverse wavelengths as of the order of 1 micron or even smaller. And it appears that variations on this small length scale are insufficient to create an optical lensing effect and thus the self-focusing instability. So the complex interference of high-order transverse modes allows us to completely suppress the filamentation in these stable cavity lasers. Let me now come to the last part about in these devices and how we can use that to generate random bit streams. Here we did simulations with a simple mode interference model. So we just consider a superposition of different transverse and longitudinal modes, which have different mode frequencies and phase fluctuations. It should be noted that the mode frequencies are, or more precisely, the longitudinal mode spacing and the transverse mode spacing are incommensurate. And that it is important because thus every combination of different modes has a different beat frequency. Moreover, we added these phase fluctuations here to model the spontaneous emission noise, where we assumed a line width of 100 megahertz, which is a typical value for these broad area devices. It should be noted that the phase fluctuations of different modes are completely uncorrelated here. This is the RF power spectrum calculated from the simulations for a single transverse mode. So we simply have a series of equidistant peaks with a free spectral range given by the cavity round trip time. So this is simply longitudinal mode beating. When we increase the number of transverse modes to 6, you see that a lot of additional peaks appear, and each peak corresponds to the beat node of a different pair of modes in the cavity. And when we increase the number of transverse modes even further, here for a number of 200, all these different beat nodes completely fill in the RF spectrum and lead to a very dense and flat spectrum, which is ideal for random number generation. Here you see the measured RF spectrum, which was determined by calculating the Fourier transform of the measured streak images. And the RF spectrum has the predicted shape, and we obtain a total bandwidth of 180 gigahertz. This is quite remarkable because it is almost an order of magnitude higher than the highest chaos bandwidths that have been obtained for semiconductor lasers, which are of the order of 30 gigahertz. So why can we surpass the frequency scales of chaotic laser dynamics? Well, the reason is that we are using mode beating, and the highest mode beating frequencies are limited by the width of the optical spectrum, which is in our case a few nanometers or about 600 gigahertz. So when we plug this number into our simulations, we obtain the black RF spectrum shown here, which has an even higher bandwidth of 500 gigahertz. So effectively, we could expect even faster fluctuations from this laser if we were able to temporarily resolve them with our measurement apparatus. So these 180 gigahertz are actually instrumentation limited. Now, a normal random number or a physical random number generator consists of 3 basic parts. The first is the physical entropy source, which is our stable cavity laser here. Then the output of the entropy source must be somehow measured and digitized with a certain sampling time tau and a vertical resolution epsilon, which gives us the raw digitized data shown here. And then we need some additional post-processing to generate the random bit streams. This post-processing is necessary because the statistical properties of the raw digitized data are usually not conform with what you expect from a good random number generator. So there are statistical biases that need to be removed by various tricks. But before we come to that, it is also interesting to take a look at the entropy rate generated by the source and to take a look where this entropy rate really comes from. Okay, so what we did here is to estimate the entropy rate using the so-called Cohen-Procaccia algorithm from the simulated time traces, where we use a sampling time of 1.5 picoseconds, which corresponds to the temporal resolution of our streak camera. Here you see the time trace for the case of a single transverse modes and without spontaneous emission noise. And the plot to the left, to the right, the entropy rate in terabit per second as a function of the vertical measurement resolution. That means the number of digitization bits. And when we increase the number of digitization bits here, we see that the entropy rate goes down again. And the reason for that is that when we look more and more precisely at the same time trace, we actually see that it is periodic. And thus, we cannot generate entropy with it over a prolonged period of time. The next case we looked at is increasing number of transverse modes to 3. As a consequence, the time trace is now completely aperiodic. And as you can see, the entropy rate vastly increases and does not go down again as for the first case. And when we additionally add the spontaneous emission noise, we see that there's a further increase of the entropy rate, and that the entropy rate scales linearly with the number of digitization bits, which is the expected behavior for such a random number generator. So what really happens in our device is that we are able to harvest the entropy generated by the spontaneous emission via the multimode interference of the cavity, inside the cavity. And this multi-mode beating process allows us to create a very fast entropy source where we can expect entropy rates in the terabit per second regime. Now, the final step is to actually generate the random bit streams, which was done with offline post-processing of the measured streak images. Here you see the digitized time trace of a single spatial channel. We used a sampling rate of 680 gigasample per second. And then we determined the differential intensity, meaning the difference between the intensity of adjacent sampling points. The differential intensity was digitized by 6 bits, of which we, however, retained only the 3 least significant bits. Here you see the distribution of the differential intensity, which is an almost perfect Gaussian distribution. And the different grayscales correspond to the 8 different combinations of the 3 least significant bits, which are almost but not quite equidistributed. And in order to remove these remaining biases, we perform an XOR operation between separate spatial channels. And well, the resulting bit streams then achieve a bit rate of 200 terabit per second. And we use the NIST and the die-hard statistical test suits, which are the standard test suits for verifying random bit generators, to confirm that these random bit streams possess the required statistical properties. Last but not least, we need to take a look at whether different spatial channels are truly independent. What is shown here is the mutual information between different channels, which is a measure of all linear and nonlinear correlations between two time signals. So the mutual correlation of a bit stream with itself is, of course, 1. However, when we calculate the mutual information with the nearest neighboring spatial channel, it drops to below 10 to the minus 6. And to put this into perspective, when we calculate the mutual information between random bit streams obtained from different lasing cavities, we see the same value indicated here by the gray line. So this shows that the different spatial channels are completely uncorrelated. In addition, we also combine the bit streams from different spatial channels. So we take the even bit from one channel and the odd bit from another channel, and we ran the statistical test suits on these combined bit streams. And also these combined bit streams pass the tests, which demonstrates that there are also no short-range correlations which would be detected by these tests. And thus we are able to extract in total 127 completely independent bit streams, which yields a total bit rate of 250 terabit per second. So let me summarize. We demonstrated record parallel random bit generation with 250 terabit per second using offline post-processing, which is almost 2 orders of magnitude faster than the previous record. An additional advantage of the stable cavity design is the simplicity. There is no need for an external interferometer or an external cavity that needs to be aligned, and also no fine adjustment of the operation parameters like temperature or pump current is needed. And it presents a new paradigm for random bit generation with semiconductor lasers. That means to use the highly multimode interference to harvest entropy from spontaneous emission noise, which allows significantly higher bandwidths and guarantees the unpredictability of the generated bit streams. And another very interesting observation is how the cavity, relatively small change of the cavity geometry allows to completely suppress the filamentation. And we are continuing to investigate different cavity geometries to see how they can be used to modify spatiotemporal dynamics. Well, eventually it would of course be great to create an actual integrated random bit generator with this principle. However, it appears that this is beyond fabrication technology, unfortunately. And it should be noted that the stable cavity is also useful for other applications, such as a low spatial coherence light source, or it could be used for chaotic LiDAR or weather computing. Thank you for your attention.
thank the speaker for this insightful and brilliant presentation. The session is now open for discussion. So any question? I don't see in the chat a question for. So everyone is welcome to. Otherwise, if not, I have a few questions.
I can ask Alfredo if you give me the floor.
Oh, sure. What I should.
No, it's okay. It's okay. I can. Yeah, I just have a quick question for Stefan. You said that there is a filamentation, a suppression of your filamentation, and associated to your design of the cavity. So in semiconductors, we know that it's the filamentation is driven by the anti-guiding factor. Could you comment on that?
Yeah. So yeah, that's exactly the process here. So that is what I described here. That the anti-guiding factor is as you know, a measure for the coupling between the gain, the carrier density, and the real part of the refractive index. In these broad array devices, this has the effect of that the spatial hole burning or the local gain reduction leads to an optical lensing effect. So these filaments are a self-focusing instability induced by the carrier-induced or caused by the carrier-induced index changes described by the anti-guiding factor.
Okay, and so the design of your cavity helps to reduce that? Yes.
So we cannot do anything about the line width enhancement factor itself, of course. But our understanding is that we can suppress this self-focusing instability by reducing the spatial, transverse length scales. So that means by reducing the transverse length, the transverse wavelengths significantly, that there are no longer strong optical lenses formed.
Okay, thank you.
Other question? If not, I'd like a few. Actually, there are two related questions. It's about nonlinear interaction in the mode. So as far as I understand, the main nonlinear interaction that has been suppressed is a kind of non-local interaction due to, I guess, diffusion of carriers. So these suppress the filamentation, and therefore all the modes are free to bit. But I would like to know more about other kind of interaction that happens in laser that are faster and local. I guess they are suppressed as well. And have you any comment on that? Is that correct? What I'm saying is the right interpretation?
Well, okay. So as far as we can deduce from our experimental results, the modes are truly independent, because all the experimental observations are consistent with our model, which is just completely independent superposition of the longitudinal and transverse modes. So if there still are some further interactions or correlations between the modes, they are small enough that we cannot see any hint of them in the experimental data.
Yeah, actually, my question was whether you had an explanation for that, but because it's clear that there is no other nonlinear interaction, but well, I was just wondering about that.
Yeah, so it's a good question. We've seen these kinds of effects for quite some time now in different cavities also. And we are still quite amazed how, in a way, easy it is to get rid of all these nonlinear interactions. We are still working on simulations to get a really a better or more detailed understanding of the processes going on. I think one other process which would be 4-wave mixing is in such a Fabry-Perot laser is also suppressed here because we have so many modes with incommensurate spacings. So we are not able, I think it's not possible to create a longitudinal index grading, which would then induce four-wave mixing processes.
Yeah. And a related question to that is, what maybe is a silly question I haven't thought about, but what about if you had the kind of chaotic resonator, such as a bow tie, where already all the modes are, well, you have a very large number of modes that are have a very, very complex superposition.
Well, one of the things that we tested is this kind of what you call chaotic resonator. For example, we looked at a so-called D-shaped resonator, which is like a circle with a part cut off. And there we see exactly the same phenomenon, that the peculiar structure of the modes here in this resonator suppresses the filamentation. This was actually observed before we started looking at the stable cavity lasers. And so, well, again, what happens is that by changing the structure of the modes, we change the spatial scales and suppress the self-focusing stability.
Okay, so I don't have any other question. If I think we can move to the next speaker. Thank you again for Let's Talk. Thank again the speaker.
Thanks for having me.
So the next speaker is Robin Mata, and the title of the talk is Numerical Training of a Convolutional Neural Network of Self-Mixing Interferometry Displacement Sensing.
Yep. Can you hear me?
Yes.
And can you see my presentation?
Yes.
Okay, so I'm gonna begin. I'm Ruben Mata, a PhD student from Onera in Palaiseau, and I'm gonna present you our work, numerical training of a convolutional neural network for self-mixing interferometry displacement sensing. A work with my two directors, François Gustave from Onera in Palaiseau and Stéphane Barlin from Institut de Physique de Nice and CNRS. So first of all, I'm gonna present you the concept of self-mixing interferometry. So you can see here a typical setup for self-mixing, which based on a standard monomode longitudinal and monomode transversal diode. So when we pump the laser, light is emitted, then it's reflected on a moving target. This is here a speaker, and some photons are after reinjected into the laser. They disturb the behavior of the laser according to the Lang-Kobayashi equation you can see here. So the red part here corresponding to the photon reinjected on the laser, they have a direct effect on the electrical field. And then the electric field, as you can see on the second equation, have an effect on the carrier density. So we can directly read the voltage to obtain the information of the displacement of the target. So on principle, when feedback, so the photon rejected on the laser is not too feedback level is not too low or too high, we can have such an experimental signal you can see on your right. So here, where upward peaks are when the target goes away by half a wavelength, and downward peak when target come closer by half a wavelength. So this is corresponding to an harmonic displacement. As you can see, so the target goes away, and then after it comes closer. So self-mixing gave us a compact system, an opportunity to build a compact system with a 3-in-1 sensor with emission, interferometry, and detection. It's also a low energy requirement because, as I said, you just have to supply the LD and recover the signal at the terminal of the diode. However, on reality, there is some physical phenomena made the signal complex and made complex the extraction of the information. The first one is the fluctuation of feedback level. So because of it, you can completely lose the self-mixing signal you have. For example, it could be because of the phenomena of speckle, so on diffusive target, and as you can see on your left, and on your right, you can see an experimental self-mixing signal. It's not really easy to reconstruct, the displacement because of the displacement. It's complex himself. So we can ask how to reconstruct the corresponding displacement with such a self-mixing signal. So there were many propositions to reconstruct, to have to increase the robustness of the system. So for example, with hardware solution on replacing the focusing lens by a liquid lens to adjust the feedback level. And so there were also software with derivating the signal and reconstruct displacements. So many ad hoc tricks for peak identification and parameters fitting. And these two solutions I presented to you, they are two complex solutions, and with them we are losing the compact advantage we have with self-mixing. So there is also, we have a different approach. So to reconstruct the signal, we use deep learning and CNN. So it's training a neural network composed by convolutional layers, and convolutional layers are layers known to be efficient in pattern recognition. So we gave him self-mixing signal and on entry, and he gave us the corresponding displacement of the target. So deep learning is efficient, but it first needs a supervised training. So you first have to give him data and corresponding truth. He learns his own rule, and after you can test it on an unknown signal. So this is what you can see on your right. Up there is a displacement and a reconstruction after a neural network computing. So the training to have it was using experimental data. It was a work made before I began to work on the project. So as I say, you first need to collect data to train your network. But in some cases, data are not available. So for example, acoustics nature of material cracks or rare events. So what happened when there is no experimental data? How can we train our network? So we tried here to train our network using simulated data of self-mixing signal. Simulate here is possible because characteristic time of laser is very fast compared to the displacement. And you can see here we use only harmonic displacement to simulate self-mixing signal and train our network. So we can adjust the following parameters. So the frequency and the amplitude of the displacement, and the origin and others like the original distance between laser and the target, the noise level, and also the feedback parameter. So the goal here is to build a sufficient data set to train our network. So after building such such a data set, such a training set, we have tested it on an experimental self-mixing signal. You can see it on your left. On the bottom, you have the original self-mixing signal, and up the displacement, the truth, so the real displacement in range, and the prediction by our network trained by simulated data on blue. So to know if to evaluate if the reconstruction was good or not, we use a statistical estimator like this graphic of correlation between the truth and the prediction. And finally, we use also the Pearson coefficient, sorry, to evaluate the correlation between the two prediction and the truth. So to conclude, I had presented you the self-mixing interferometry, which give us the opportunity to make detectors compact and with low energy requirements, with a sub-wavelength precision, potentially high bandwidth because time of photon out of the laser is less than 100 picosecond, and also a versatile approach because there are many applications we can do with it. But self-mixing interferometry gave us a very tricky signal analysis. So there is two big problem with it. First, it's the reconstruction when we have self-mixing signal, the reconstruction of the treatment of the signal to reconstruct the displacement. So here we used deep learning and CNN, which gave us an excellent and robust reconstruction quality, but need training before. And another advantage, it's a real-time processing. And as I said, there were two problems with self-mixing interferometry, and the first one is to have a signal to have a real signal. So our future work is to try with a multi-canal setup to be sure to have a signal of self-mixing to refine the displacement. So thank you for your attention. And if you have questions.
Yeah, thank you for this very nice, interesting talk. I'd like to invite the audience to ask questions. Is anybody? Oh, if not, I have two quick questions. The first is, as far as I understand, you trained this neural network with a known signal, and then you demonstrated that it works. My question is, how general is this? Do you have to make some specific assumption on the signal you are going to test? So, for instance, the bandwidth of the displacement, or once you train with a signal, you have a much broader range of the signal that you can successfully reconstruct. I hope the question is clear.
Sorry, I will try to answer. So the answer is not good. You can ask me again. So we use simulated harmonic signal. For example, on frequency, we use signal between 10 and 100 hertz on frequency, and we can test it with signal with very big sorry, very much frequency. So, for example, with a 500 Hz frequency, and what you have to know is that the network doesn't have any time scale. So we just see points and with no time scale. So if you just change, for example, your sampling frequency, when your sampling frequency, it will work like another one. So it's very robust. It's a very robust system.
So you don't need to train again the system. Once you have trained it, is
no.
okay.
You have to train your network only one, but you have to be sure that the training it's a good quality. It's a good quality training, and after that you test on experimental signal, on unknown signal, and you can compare the quality of reconstruction.
Okay. Okay, thank you. So I have no other question. Nobody ask questions. Okay, so then thank you again, and
Thank you.
We move to the next talk.
Yes. Just give me a second.
So the next speaker is
Okay.
okay, I don't see the name. Madam Rimoldi, and it will give a talk entitled Dynamics and CW Stability of a 3.5 on silicon hybrid laser with frequency selective mirror.
Okay. Can you see it in full screen?
Yes.
Okay. So good morning. My name is Cristina Rimoldi, and I'm a postdoc at the Department of Electronics and Telecommunications at Polytechnique di Torino. And as introduced by the chairman, today I will be talking about the dynamics and CW stability of a 3-to-5 silicon hybrid laser with a frequency selective mirror. So this is the outline of my talk. After spending a few words on the motivation of this work, I will talk about the laser that we are considering and its modeling. I will then introduce the possibility of adding an optical feedback to the system, and I will then draw some conclusions. So silicon photonics is a disruptive technology that focuses on the integration of photonic devices in silicon-based circuits. This to the aim of transforming typical electronic and photonic applications, for example, in the context of data center interconnects, sensing, and high-performance computing. Now, some of these devices can be of use in the context of optical transceivers. However, here there is an open issue, which is given by the fact that there are spurious back reflections arising from the passive parts of the circuit. And in this context, optical isolators are not considered efficient enough for the industrial market. Therefore, there is a need for a laser that is as tolerant to optical feedback as possible. Now, this is the device, the laser that we are considering. It consists of a 3-to-5 multiple quantum well HR-AR reflective SOA that is edge coupled to a silicon photonic mirror. Silicon photonic mirror that is based on 2 couple rings here. It is this 2-ring configuration that provides narrow reflectivity in frequency, as also illustrated in this picture. And the coupling coefficients of the 2 rings are chosen as equal in order to maximize reflection. The output power is collected here through the coupler. And we also include the phase section right here in order to have the possibility of introducing a phase shift on the CW lasing frequency. Finally, Rx here is a condensed reflectivity that accounts for all spurious back reflections. Now, an error reflectivity implies a narrow optical line width and a higher stability towards optical feedback. However, it also implies a lower free spectral range, and therefore also a higher probability of competition between cavity modes. Our focus in this work will be therefore to utilize a model that is both efficient and able to correctly account for this error reflectivity. In contrast, for example, with a Lanko-Bayesi approach. And we will be studying the effect of the reflectivity FWHM on the laser stability. Now, our model is a set of time delayed algebraic equations where E here is the field that is entering the silicon photonic circuit. AC1 is the field that travels from the first to the second ring. And AC2 is the field that is leaving the splitter. And N here is the carrier density. Now, for a full derivation for especially the equation for the field E, I would like to point you to this reference here. Here instead, I would like to highlight the most important parameters for our analysis. In particular, I is the bias current, and delta phi is the phase shift that is there due to the presence of the phase action that I illustrated earlier. And we use delta phi to control the laser detuning under the reflectivity bandwidth. In the frequency domain, this system has a boundary condition at the AR coating facet of the reflective SOA, which is given by this expression here, where in particular AC2 has this dependence on the field E, where RF is our effective reflectivity, accounting for the presence of the two rings, where in particular we have this expression, and gamma C1, T1, C2, and T2 are functions of the ring radii, losses, coupling coefficients, and group velocities. And they are derived from the drop transmission coefficients of the two rings. We can extract the CW solutions of the model consisting in this set of laser modes, each corresponding to a specific carrier density value. Our aim in the following will be to study the stability of the laser mode with the minimal carrier density. We can also perform a linear stability analysis of the system in the frequency domain by introducing a perturbation of this sort. When we apply this perturbation to the model equations, we obtain this Jacobian matrix right here. And it is the zeros of the Jacobian matrix, of the determinant of the Jacobian matrix, for example, that are illustrated here in this picture for a specific choice of parameters, that give us information on the laser stability. Now, in our convention, the imaginary part of the zeros relates to the damping factor, and the real part relates to the frequency. As we know, the zeros of the determinant are also poles of the modulation transfer function, and this allows us to easily associate the poles with the lower damping factor with relaxation oscillations and side mode competition or photon-photon resonance, as also illustrated in this picture here for the intensity modulation response obtained dynamically. Now, when the imaginary part of one of the poles becomes negative, we color the pole in orange, and the system becomes unstable. Now, there are several control parameters that we can act on when performing numerical simulations in the absence of external feedback. For example, we can perform sweeps in terms of bias current. We can also perform sweeps in terms of laser mode position, and we can perform the same analysis for a range of FWHMs for the modulo square of the effective reflectivity. This always considering equal effective lengths. So, for instance, if you consider an FWHM of 3 GHz, and we perform a sweep on the tuning of the laser mode, we can obtain a picture of this sort for the ring spectra. Here we can observe in this area the presence of regular oscillations. If we now superimpose the results from a linear stability analysis, we can observe that there is a very good agreement with the prediction of instability. We can now focus on a specific value of the tuning, for example, at minus 2.8 here, and slowly increase the current from 20 to 200 milliampere. And here we can clearly observe that instability in this case arises from a condition of resonance between relaxation oscillations and the beating between adjacent lazy modes, beating that is illustrated with the black dashed line. On the other hand, if we increase the FWSM to 11 GHz, we can observe that there is also another cause of instability, which is related to side mode competition. Here, the red dashed line corresponds to the separation between the lazy modes and the lazy mode and its side modes at threshold. We can now perform a switch at the same time on the tuning of the lazy mode position and the current. This for different values of FWA sensor, resulting in these integrated green maps. Here in particular, I've highlighted with the white dashed line the border of instability derived from linear stability analysis. The yellow region here and also in the other plots corresponds to a region of multi-mode regime where the CW solution has become unstable. And these three regions here that are blue, but are also encompassed by the border of instability, are simply regions of mode hopping that are also not to be considered for our operational purposes. We can then now plot the range of stability in delta nu for any bias current. And here we can observe the clear presence of an optimal middle point, which implies a trade-off between the two causes of instability. On the other hand, we can make some considerations by looking at the poles with the minimum damping factor. These poles are associated to relaxation oscillations for FWHM equal to 3 GHz, and most of the time to photon-photon resonance in the other cases. Now, these poles, also in the stable region, are the ones that are more likely to lead to instability when we introduce optical feedback. And if we look at the behavior of the damping factor in scale now, we observe that the larger is the FWHM, the lower is the minimum damping factor, which implies a higher probability for the system to become unstable for larger perturbations. Now we want to see what is the effect of introducing optical feedback in one of these stable cases. So we put ourselves in this condition, in this parametric condition here. And this is the picture of the solitary laser pulse in absence of optical feedback. When we introduce optical feedback with a very low value of external reflectivity, this implies the emergence of this external cavity pulse. And if we slowly increase the external reflectivity, we can observe that this external cavity pulse push down on the solitary laser pulse. These lines represent the trajectory, eventually giving rise to instability when an external cavity pole becomes resonant with one of the solitary laser poles, especially the one with the minimum damping factor. You can see basically the same thing also in this picture here for the ring spectra. This kind of behavior is similar for other FWHMs and also for other values of the tuning, which allows us to conclude that instability develops due to a pole that is either close or the same as the one responsible for instability without feedback. Now, if we want to focus on the critical feedback level right here and see its behavior as a function of delta nu for the different FWHMs, which are here represented in different colors, we can obtain this plot. And here a few considerations. So overall, as a general trend, we can observe a decrease of the critical feedback level for increasing FWHMs, which makes sense because we have an increased effect of photon-photon resonance. Then this first peak here is developing in a condition of a high damping factor for the solitary laser in every FWHM configuration. And right here, the destabilization is mainly due to external cavity modes. The second peak here is instead simply due to a favorable mode configuration in the solitary laser, where very simply put, the neighboring lasing modes are particularly distant from the one at minimal threshold. So as you can see, the second peak changes its position depending on the FWHM that we consider. And this allows us to identify this other region as the best region for design for ever reflectivity. And further, we can suggest that if we consider a lower, still realistic external length, this may lead to a higher stability. So these are my conclusions, and future work will consist in the investigation of lower external lengths and in the application of the same kind of analysis to other laser configurations. Thank you for your attention.
Thank the speaker for this very clear presentation. Any questions? Let me ask a very, very simple question. So it's correct to say that if you had a higher and a higher Q factor in the feedback resonator, so you in principle are able to control any instability. So that the key for practical application is to have better and better resonator.
Well, I mean, in our case, we observe the presence of a trade-off, if you saw, like if we consider like a reflectivity that is too narrow, then we have also to pay attention to the effect of relaxation oscillations. So, I mean, our observation when we look, this study is mainly focused on the effect of the reflectivity FWHM, always at parity of effective length. So yeah, I mean, in this case, we are just focusing on the width of the reflectivity and seeing what happened just by looking at that. And yeah, if we have a trade-off effect, so we have to be careful about that.
Okay, thank you. Actually, the answer was there. Thank you, and let's move on to the next speaker. So the next speaker is Dr. Well, is the next speaker there? Yes. So the next
speaker is somebody from
is Danilenko, Dr. Danilenko from.
No, I'm not doctor. I'm second master.
Also. Well, welcome. So the title of the talk is Effect of the filter feedback on the memory capacity in a photonic reservoir computing.
Good morning. I'm Gleb Danilenko from ITMO University, St. Petersburg, Russia. The topic of the report is effect of a filtered feedback on the memory capacity in a photonic reservoir computer. This work was done jointly with Georgia Tech Lorraine, Center Supelec, and University de Lorraine. In this work, we study the performance of a photonic reservoir computer based on the semiconductor laser with high and low pass filter in the optoelectronic feedbacks. So filtered feedbacks means that the signal of a feedback is frequency filtered. Reservoir computing is a data processing paradigm based on a complex response of a dynamical system called the reservoir to the input signal perturbation. This response depends on the input signal and the previous state of the reservoir. Thus, the reservoir computer system possesses hidden memory similar to classical recurrent neural networks. One of the most important characteristics of a reservoir computing is a memory capacity, which measures the ability of a reservoir computing system to reproduce the input at the previous delayed time. The absence or small value of a memory capacity can lead to a deterioration of a system performance, especially in forecasting tests. Reservoir computer system consists of 3 layers, labeled as input, reservoir, as I said before, and output. The advantage of reservoir computing is the simplicity of a system training performed by adjusting on the output layer of a system. A reservoir computer system based on a feedback architecture relies on a time delay reservoir computing approach. Here, a single physical nonlinear node is used in conjunction with virtual nodes distributed in delayed feedback loop. A photodiode detects the laser signal when it's filtered at first by high pass filter, then low pass filter, and after it's amplified. Next, the filter signal is added to or subtracted from the pulse current applied to a driver laser. Finally, it closes the time-delayed optoelectronic feedback loop. The input data is entered by modeling the pump current by one input value per one delayed time. At first, each input sequence element is multiplied by a mask. Masks aim to keep system in unstable state. Dimensionless equations based on a laser with optoelectronic feedback account to high pass and low pass filters in optoelectronic feedback. The first equation described the intensity. The second describes the high pass filter with characteristic time value tau h, which is equal to the inverse of a cutoff frequency of a high pass filter. The third describes a low pass filter with characteristic time tau L, which is also equal to inverse of cutoff frequency of a low pass filter. And the fourth characterizes the active medium and feedback. Memory capacity characterizes the system's ability to reproduce entered input data. We first performed a linear stability analysis to determine the Hopf bifurcation borders, when range of a feedback strength and power parameter for a reservoir computer system numerical modeling were chosen based on the calculated bifurcation boundary for each low-pass filter cutoff frequency. The reservoir's memory capacity was calculated as correlation between the pass inputs and their values extracted from a reservoir. Figure shows the 2D map of a system's memory capacity for different values of a low-pass filter cutoff parameter along with Hopf bifurcation border. Changing the bandwidth affects the bifurcation structure. Firstly, it takes on a complex shape and then relatively flat. The 2D maps are asymmetric with respect to the feedback sign. With a decrease of a cutoff frequency of a low-pass filter in a feedback loop, we see that the memory capacity decreases. The maximum value observed in the vicinity of a Hopf bifurcation border. Moreover, Moreover, the maximum value of memory capacity is observed for a negative sign of a feedback strength for each tau L. The area with largest value of memory capacity is light green. The spectrum of eigenvalues for a stationary state was calculated for maxima of a memory capacity in each case. Let's look at the A figure. The spectrum can be characterized as two-peak structure with high contrast between peaks in the upper A figure. A multiply peak figure with low contrast between on the middle A figure and a single peak structure presented on the lower figure. So changing low cut frequency leads to a change in the spectrum. The most interesting situation is observed in the middle figure, corresponding to the maximum memory capacity among the analyzed parameter. Many eigenvalues of a spectrum can be characterized as having small damping, and overall spectral shape can be considered as a relatively flat top. While the spectrum is symmetric in relation of a feedback sign, it cannot explain the asymmetry of a memory capacity. We found that the average distance between a pseudo-continuous spectrum and imaginary ASICs is well correlated to the memory capacity. We performed the pseudo-continuous approximation of the eigenvalue spectrum under the assumption of a long delay, using the approach described by Janchuk and Wolfram to further investigate the correlation between the spectral properties of the reservoir and the memory capacity. Under this approximation, the eigenvalues are considered belonging to the pseudo-continuous spectrum. The pseudo-continuous spectrum is symmetric with relation to the real ASICs and the sign of a feedback strength. We introduce an average distance d between the real part of the eigenvalue spectrum and the imaginary ASICs to characterize the flatnesses of a spectrum and its average damping. This measure does not depend on the delay time. This average distance characterizes both proximity of a spectrum to the ASICs and its flatness. The flatness of a pseudo-continuous spectrum and its proximity to the imaginary ASICs explain the increase of the memory capacity when a filter cutoff frequency is changed. Thus, changing of the low pass frequency leads to a change in the pseudo-continuous spectrum. The overall spectral shape affects the average distance d between the real part of the pseudo-continuous eigenvalue spectrum and the imaginary ASICs. Reduction on the imaginary of the average distance d entails an increase in memory capacity without regard of the feedback sign. The area with the largest value of the memory capacity for each tau L corresponds with area with the smallest value of the average distance d. An enhance of memory capacity in case of a negative feedback may be associated with the absence of a resonance between the eigenvalues frequencies and the input signal frequency, and more efficient modulation in the case of a positive feedback. Summary. Changing the low pass filter cutoff frequency alters the shape of the eigenvalue spectrum. Reducing the distance between the real part of the pseudo-continuous spectrum and the imaginary ASICs correlates with the increase in the memory capacity of the optoelectronic feedback reservoir computing. Thank you for your attention.
Thank you very much for this interesting talk and with this connection, explanation of memory capacity that is in my opinion, still very obscure notion in the field of reservoir computing. And yeah, are there any question about that, please, the audience? So I see a comment, maybe. So, No questions? So, well, let me ask you a general question. You've shown that by understanding this connection, you may have a path to improving the performances of this system. This is very interesting, but have you an idea how far you think you can go with this approach in terms of improving the computing power of this reservoir system?
Why did we go this way? It was just a task for my introducing in with visual computing from my supervisor, and we could have supposed what it would cost with the result. So it was like touch a finger in point.
Yes, but yeah, it's very nice. Anyway, well, if there are no other questions, let's thank the speaker again and move on to the next. So the next speaker is
Hi.
So
can you see the presentation fine?
So is guess Ana Ribeiro? Yes, who will present a dual section massively mode locked quantum dot laser with continuous wave optical injection. Please.
So good morning. My name is Anna. I'm a PhD student at Heriot-Watt University, and I'll be presenting my research group's work on a dual section passively mode locked quantum dot laser under continuous wave optical injection. So optical injection has been thoroughly studied throughout the years in quantum dot lasers. And in particularly in mode locked quantum dot lasers, it has shown all of the great benefits, in particular, the improvement of the temporal stability of the pulses, which leads to a reduction of the timing jitter. A few other benefits are also a great reduction on the timing bandwidth product, as you see here, from the spectral narrowing that occurs with optical injection, and also the possibility to tune the repetition rate of the pulses in case of a dual tone optical injection. But the optical injection is quite a complex process, which not only depends on multiple factors such as the injection characteristics, the injection power, and the injection wavelength, but also in the bias conditions of the injected laser. Usually, you see in papers optical injection produced as bifurcation maps, where you can see all the different regions of the behavior of the quantum dot laser. These maps are usually shown in the form of injection power versus detuning between the injection wavelength and the wavelength of the injected laser, which in the case of a mode-locked laser, it's simply the closest optical mode to the injection wavelength. There has been one particular study of a semiconductor laser under CW injection who has predicted that it may be possible to obtain different regimes with optical injection, such as Q switching and double pulsing, depending on the S parameter, which in this case is the ratio between the absorption saturation energy and the gain saturation energy and the injection strength. So, our study will be around how exactly optical injection affects the laser that we have in our lab, what kind of regimes can we find, and how we can characterize it. So this is our optical injection setup. The device under study is an 8mm two-section passively mode-locked quantum dot laser, and the master, the CW laser that is the light is being injected in the quantum dot laser, is a narrow line with just commercial CW laser. To lock the quantum dot laser to the CW laser, we must match the injection wavelength to one of the optical modes of the quantum dot laser. So we tune it in small wavelength steps to match one of the optical modes, and the quantum dot laser is considered to be locked to the CW laser when there are no visible beating nodes in the RF spectrum. So next I'll be showing the experimental results for the optical injection of our laser. We have observed 3 different regimes that I'll be speaking about next. The first one being Q switching. So at these bias conditions that you see here, and also in some other bias conditions regions not shown here, we have found that with optical injection, we go from having a perfectly mode-locked quantum dot laser to having a pure Q switching behavior with approximately 1 gigahertz peak on the RF spectrum. When we look at this on the optical spectrum, we also see that there's significant spectral narrowing, and also that we can tune this Q switching regime with the injection wavelength. In fact, Q switching regime had already been reported in free-running, not injected quantum dot lasers, usually on the form of Q-switched mode locking, and there are also a few reports of pure Q switching. But why can we induce this Q switching regime with optical injection? Well, under the injection of this narrow linewidth CW laser, the injected photons will favor the modes closest to the injection wavelength, thus leading to the spectral narrowing that we see. And this spectral narrowing implies that only a restricted set of quantum dots are part of the laser emission, and that leads to 2 other effects. So, as there is a narrower subset of quantum dots present, there is also a smaller distribution of the quantum dot sizes. And when we do the link between Q switching and relaxation oscillations, and we know that as we increase the homogeneous broadening, we also have more pronounced relaxation oscillations, we can say that in this case, we are creating a sort of similar situation where the inhomogeneous broadening is somewhat being reduced. And so this promotes the more pronounced relaxation oscillations, which are the foundation of the Q switching regime. Also, adding to this, as we do have the narrower subset of quantum dots, we also reduce the intensity required to saturate the absorption. And due to a continuous optical injection, the few quantum dots in use may also be experiencing some partial bleaching, which further reduces this absorption saturation energy. Returning to the graph I had shown earlier, you can see how, being that the S parameter is the ratio of the saturation energies in the gain and absorption section, that since we are reducing the absorption saturation intensity, we are in fact promoting possibly the appearance of a Q switching regime, as you see here. Then next, we try to see exactly how the Q switching repetition rate changed with different variables of the optical injection process, starting with the injection power. And we saw that the Q switching repetition rate increases as the injection power increases in a somewhat linear trend. We believe this to be because the increasing number of photons with injection power will accelerate the pulse buildup process and thus decrease the time in between pulse emission, increasing the repetition rate. Then next, we try to see how the repetition rate changed with the absorber reverse bias. And once again, we saw a linear increase of the Q switching repetition rate in a somewhat linear tendency with the increase of the absorber reverse bias. And why could this be? Well, as the absorber reverse bias is increased, the absorber recovery time is decreased, which will lead to the peak of pulse emission being increasingly earlier and thus decreasing the time in between pulses and increasing the repetition rate. When we try to evaluate the Q switching repetition rate in terms of the gain current of the quantum dot laser, we found a much more complex trend, which we believe could be the interplay between 2 different effects, the effect of the differential gain and the gain recovery time. Starting by this first region where you see the repetition rate decrease and then somewhat stabilize, we believe this to be due to the effect of the differential gain. So once again, when we do the link between Q switching and relaxation oscillations, and we know that the relaxation oscillation frequency is proportional to the square root of the differential gain, we also know that in quantum dot lasers, the differential gain drops quickly with current and then tends to stabilize. And so it's this effect that we believe to see here. But then as we continue to increase the current, we see then that the repetition rate starts to increase. Well, we believe that in this case, the effect of the gain recovery time starts to be more dominant. As the current increases, the gain recovery time is becoming shorter, and this would lead to the population inversion being reached more quickly, thus reaching the conditions for pulse emission earlier and increasing the repetition rate. However, there's also maybe another plausible explanation for how this trend is so complex. It could be just actually related with the optical injection process, particularly the separation between the CW wavelength and the quantum dot laser's closest optical mode, which might be varying with the gain current and thus affecting the locking effectiveness. So there have been other regimes that we also found at different bias conditions of the quantum dot laser. At this particular set of bias conditions, we saw that with injection, we can actually improve the mode locking. So with injection, we induce a mode locking with a slightly lower repetition rate and with a much better signal-to-noise ratio when comparing with the free-running case, and then a reduction on the RF line width. In the optical spectrum, we also see the spectral narrowing that we were seeing earlier with Q switching. And once again, we see that this regime is tunable with the injection wavelength. Going further to different values of the reverse bias, much lower values actually, you see how we were also able to find different locked regimes, a locked multiple pulsing. In fact, we saw both double pulsing and triple pulsing at two different bias conditions with pulse separations of approximately 30 picoseconds. But multiple pulsing has already been reported in free-running quantum dot lasers, usually at higher gain currents. And the higher gain currents, together with the decreased absorber reverse bias in this case, creates the opportunity for multiple net gain windows, which leads to multiple pulses being formed. But how does optical injection induce this multiple pulsing? Well, we believe it could be because the optical injection, as I had said earlier, may be reducing the absorption saturation energy and thus facilitating the emission of additional pulses with lower energy. So in summary, we found for the first time experimentally a pure Q switching regime in an optically injected quantum dot laser. This regime is tunable in repetition rate via gain current, absorber reverse bias, and injection power, and also via wavelength by tuning the injection wavelength. We also found two other regimes at different bias conditions, which we believe will give new insights into the complex dynamics of the optical injection process. There are some possible applications to this. First of all, we have shown that optical injection increases the versatility of the quantum dot laser, creating the possibility for a controlled switching between different regimes, which could mean that optical injection could be useful where a pulse-on-demand single laser system is required. Besides this, optical injection also increases the usability of the laser as it induces a Q switching regime, which otherwise has not been observed in our quantum dot laser when not injected in the threshold region. And in fact, Q switching has multiple published applications, such as time domain fluorescence measurements. Thank you so much for your time, and I'm happy to answer any questions.
Thank you for this very clear presentation, and I invite the audience to ask questions. So you can also write in the chat if you have questions.
Hi.
Yeah.
I have a question actually. I'm not familiar with quantum dot lasers, but I was wondering if, because you said that this behavior is induced by the saturation energy of the quantum dots. And so do you know, would it be possible to design the quantum dot to favor that effect, or on the contrary, to limit it? Because I understand that you've worked with one kind of quantum dot lasers, but what about the design of the quantum dot active region, for example?
Yes, in fact, we know for a fact that the design of the quantum dot laser heavily affects how it will behave under optical injection. Actually, one of the things that we did see is that, for instance, quantum dot lasers with longer absorber sections favor or not the Q switching appearing in free running lasers. So we believe that these results that we did get when optically injected are linked to the structure of this particular quantum dot laser, and it doesn't mean that another quantum dot laser will have this exact behavior under optical injection.
Okay, I understand. Thank you.
Thank you.
Any other questions?
I have a short question, maybe.
Yeah, sure.
So first of all, thanks for the nice talk.
Thank you.
I have a short question about this regime where you observe the narrowing of the bit note in the RF domain. So near the end, when you observe the narrowing of the RF signal at 5. Yeah, that one. So this would mean, if I'm correct, that your laser is locked to the injected signal, and at the same time you observe this narrowing of the spectrum. But my question is, did you maybe study the influence of the injected power, and did you maybe observe different regimes, for perhaps even the broadening of the laser spectrum?
Actually, the injected power does have a high influence on the behavior of the laser. We found that particularly for a few specific bias conditions of the quantum dot laser, that if we have a lower injection power, we can see a locked mode locking as we see here. But if we have a higher injection power, we can induce Q switching. So the injection power does influence the kind of regime we can obtain. In this case, for example, if we were to, this case was obtained with the low injection power of approximately, well, I can't say for sure, but only like 100 to 200 microwatts. And if we were to increase immensely the injection power to about 1 milliwatt, we wouldn't be able to get this nice results. Actually, the locked mode locking wouldn't work then.
Okay, thank you.
Thank you so much.
So if no other question, I would let us thank the speaker again, and let us move to the last speaker of this session. Is Dr. Shariful Islam, who will deliver a talk on bound pulse state in a multiple quantum wave laser subject to delayed optoelectronic feedback.
I think everyone can hear me.
Yes.
So, one correction, I'm not a doctor, I'm a fourth-year PhD student. Okay, let's share my screen. Everyone can see my screen, right?
Yes. We cannot hear you very well. If you can talk a little bit louder.
Okay. Good morning. I think the audio is better now.
Yes.
Thank you. So welcome to the presentation on bound pulse state in a multiple quantum wave laser subject to delayed optoelectronic feedback. I am the presenter, Mohammad Shariful Islam, a PhD student with Georgia Tech. So this is the outline of my presentation. So we'll first discuss the background of the project, followed by some interesting applications. We'll then dive into the experimental details and present the experimental observations. Finally, before concluding, we'll introduce a brief account for the experimental observations in terms of the theoretical understanding. So the primary motivation of this work is a report on gain switched pulsation under optoelectronic feedback. So when the laser diode is close to the injection threshold, a gradual accumulation of the carriers into the gain media can push the laser momentarily above the threshold, where the carriers then can contribute to the stimulated emission of a bunch of photons that can constitute a pulsation at loop delay frequency. This pulsation was attributed initially by the authors to a bootstrapping mechanism due to the fast carrier accumulation in the gain media compared to the due to the fact that the carrier accumulation in the gain media is slower compared to the emission of photon, which is much faster in scale. Another motivation is with similar setup, similar optoelectronic setup, but in this case, the pulsation comes from the natural oscillation frequency of the laser. So in case of the second class of pulsation we're presenting in this slide, the pulsation appears at little higher injection current compared to the previous one, where the pulsation appears exactly close to the injection threshold. So some of the applications we can present it here. We have recently reported the chance of the gain switched pulsation close to the threshold to produce micro frequency comb and compare it to the afro pulsation that appears at higher injection current. Our conclusion was that the gain switched pulsation fundamentally offers a much higher resolution compared to the afro pulsation in a limited bandwidth. So at least in case of micro frequency comb, both type of pulsation have their applications. There are other applications such as in communication and sensing. So moving on, this is the experimental setup we have used. It is similar to the one we have shown in previous slides. So it's optoelectronic feedback. Light is photo detected, properly amplified, and feed back to the injection terminal through a bias T. So as expected, we have observed both the gain switched pulsation, or the f-tau pulsation, what we can call it, and the natural oscillation pulsation, or the afro pulsation. But under but we have noticed that a peculiar form of bound state in the vicinity of laser injection threshold, which is the focus of the current presentation. The experimental setup is based on a multiple quantum well laser diode, where the loop delay is 33 nanoseconds. So this is the results, the primary results that we are going to discuss. So the initial pulsation naturally appears just below the threshold, but above the threshold we see multiple transition from one bound pulse state to another. So what that we are calling a bound pulse state. So a bound pulse state can be defined as a state consists of two or more pulses propagating with a stable interval separation. This is the center part of our discussion, which shows that the evolution of multiple bound pulse states within the pulsing at f-tau and pulsing at afro. So we can see that at the beginning there is the pulsing at f-tau, and at higher injection current the pulsing at the natural oscillation frequency, and in between this what we are trying to describe as the bound pulse state. So such localized structures are often reported as a bistability between on and off state, but never to our knowledge been reported as a gradual progression from one bound state to another. Although the theoretical understanding is underway, we have observed that under the saturable non-linearity in the amplifier, this type of pulsation with a positive oscillator feedback is common for multi-quantum well laser. And moving on to the characterization of such pulsing, we can check that the pulsing states, but the traces clearly shows that the cases of bound states are not instances of harmonics, because we can see clearly the modulation, which indicates the pulses are clustered together. This shows the RF spectra over a range of injection current. So a more global picture compared to the previous two slides where we picked some of the traces. We see pulsing frequency at a higher injection current follows 2:1 ratio with the natural oscillation frequency, although this is not the case when we are close to the injection threshold. We have checked the system by ramping the injection current up and down and found the presence of hysteresis near the threshold. So in this area, we see the F-top pulsing and the bound pulse states, and when we move the injection current in one direction and the other, the appearance of the bound pulse state changes in terms of injection current. So one is speculation from the current state of the modeling for the bound pulse state is that in the vicinity of the laser diode threshold, the bifurcation becomes subcritical, which makes the folded bifurcation structure similar to the localized structure that we are seeing. However, this speculation still requires further testing in terms of modeling. So this is the spatiotemporal reconstruction, which we present to confirm that the pulse structure are indeed bound pulse states. So we can see over several round trips that the separation between the pulses in the case of the doublet pulsing and the triplet pulsing remain the same, and the repetition from one structure to the next one also remains the same, which clearly shows that these are instances of bound pulse states. So in conclusion, we show two distinct set of pulsing mechanism under the same experimental configuration. One is dominated by the external loop delay frequency, and the second is the well-known natural oscillation frequency of the laser. But more interestingly, we show a gradual progression of bound pulse states that mediates the progression between these two mechanisms. This is the end of my presentation. So I'd like to welcome any question.
So let's thank the speaker for this interesting and insightful talk. Session is open for questions. Yes? So, Federica, you are asking question?
No, I'm just preparing to announce the following.
Okay, if no questions, let's thank the last speaker and all the speaker, and the session is closed.
Okay, so thank you, Alfredo. So now we can have a short break. The next session on innovative laser structure will start at 11 o'clock. So we have time to see if the speakers are there, and we just take 10 minutes break. So see you at 11. So Stefan? You can check, Stefan, if you are, I think, yes, you are still online. So you can check if the different speakers are with us.
Recording stopped.
Alfredo, tu veux essayer de charger tes slides? Stefan, if you want to check if the speakers, I think Alfredo is, of course, with us, but for the others,
Good morning, Frederic, Stefan.
Good morning.
Yeah, this is Guillermo Carpintero.
Yeah.
I will be speaking in place of Jessica, my PhD student. She had a personal issue, and I will take her place.
Okay, this is the last talk, right?
Right.
Okay. Okay. So I think because the talk just before you has been cancelled, we are gonna put your talk at 12:15. Okay.
No problem.
12:30, and we will have more time for lunch.
Okay. Perfect.
Okay. Yeah.
Yeah. Yeah. I thought that would be a sensible thing to do. And I guess Stefan will have, or you will have to announce at the beginning of the session.
Stefan, we don't hear you. Your mic is off.
Yeah.
Now you can hear me, hopefully.
Yeah.
Okay, good. So the only one that I can't find in the audience at the moment is the fourth speaker, Anirudh Pami. Do you have any news of him or her?
You don't see the speaker in the list?
No. Or maybe I'm looking for the wrong name. No. Okay. So
Is there anybody from C2N giving this talk at 12 o'clock on time symmetric and symmetry broken pulse sequence in a spiking micropillar laser with optical delayed feedback in the audience? Okay, so let's see.
yeah, it would be great if somebody turned up. Okay, but maybe they just logged out during the break. We'll see.
Is there anybody in the audience working with Sylvain Barbet and giving this talk at 12 o'clock? Okay, so we will see.
It's they still have some time.
Yeah. Alfredo, can you hear us?
I'm seeing Sylvain Barbet just joined us. Sylvain, I didn't see, I think Anirudh Pami in the audience. Is she going to give her talk, or is somebody else from your group?
I'm going to give the talk.
Okay, you are going to fill in. Okay, good. Thanks. That's
okay, so we all set.
Okay, so apart from the talk by Dan Lenstra, which was cancelled previously, then everybody is around. That's great.
All right. We have everybody for this session except the Lenstra.
Yeah, exactly. Okay, Frederick, I propose we start now.
Yeah, I think it's
Great.
we are on time. Yes.
Okay, great. So my name is Stefan Wittner from Central Supelec in Metz, and I'm sharing this session on innovative light emitting structures and applications. So it's my pleasure to announce our first invited speaker, which is Alfredo Di Rossi from Thales Research and Technology, who will talk to us about nanoscale photonic sources of coherent light. Please,
thank you very much for the introduction, Mr. Chairman. And first of all, can you see the share screen? I'm not sure that this works.
Yeah, we see your presentation.
Great. So I can start. So my talk is actually about photonic crystal, an old topic. But the goal of my talk is that in the end, this is not to convince you that this is in the end not an issue. So it's actually a work, collective work with my colleagues, Sylvain Combry at Thales and Fabrice Ranieri at Citizen, and also collaboration with Fabien Bretnaker at École Normale Supérieure Paris-Saclay. So Thales, I'm from Thales, and Thales, whom may not know, is a company mainly focused on electronics, so optics. Optics is because we actually have a long story in trying to in investigating how to use optic for processing signals more efficiently than with electronics. So these are studies dating back in the 90s. So what I'm showing is using optical correlation for some kind of our typical application. That was long ago. And now what we are doing is one of the topics we are interested in is a miniaturization of photonic devices. So here you see some example of recent photonic devices that have one thing in common. They are all made using photonic crystal cavities. And you have an optical random access memory based on a bistable optical cavity. You have a Raman laser, a self-pulsing laser, and a nano-scale laser diode. They have all in common one thing, is that the power level or the energy level is in the order of microwatt, femtojoule. And they're all micron scale. So this is, in this context, we drag our motivation, that is to find out all what we could, is to use this technology as a way to miniaturize and increase the efficiency and compactness of photonic circuits. So photonic crystal is a dielectric, and is a dielectric that is periodically modulated, and is a very general concept that works also in the microwave domain. Actually, that was the very first demonstration. And for a long time, it has been very challenging to build high-quality optical resonators using photonic crystals. Then a breakthrough went about 15 years ago, when it was understood that design plays an important role. And today it's possible to achieve a Q factor in silicon about 10 million, which as far as I know, is the largest Q factor in any silicon resonator, meaning storage time of 10 nanoseconds in a micron size volume. And that this is not all about silicon. These photonic crystals can also be made with many other materials, thereby increasing their functionality. It has long been said that it's very difficult to connect, to interface photonic crystal optically, but this is solved. So here are some examples how you can inject light efficiently to a photonic crystal using adiabatic taper merely. And you can go very, very far away with the coupling efficiency. So for instance, this last example is from Harvard. They claim up to 95% coupling efficiency. And finally, the most worrying criticism about photonic crystal was their complexity, and their sheer scale. But with the progress of CMOS fabrication, now the spatial scale of photonic crystal is perfectly accessible to CMOS. And actually, this is a complex structure made a few years ago with the photonic crystal and also a sort of CMOS circuitry to control the propagation of light. But what is special about the photonic crystal cavity? Photonic crystal cavity is different from other kind of resonator. And here, let me point this out. So if you consider first a ring, a Fabry-Perot, or a whispering gallery mode resonator, they have all in common these properties. First, they have a large number of modes. And second, the field distribution of each mode is uniform. So for instance, in a ring resonator, the azimuthal field distribution is constant. Let's now consider a photonic crystal resonator. Photonic crystal resonator number of modes can be very small, can be truly single mode actually. In contrast, field distribution is absolutely not uniform. And what is interesting is that this can be controlled by design. And the volume of the mode can be as small as close to the diffraction limit. That is basically half the wavelength in the material. So this is the motivation, because this means that the concept to build and so what is interesting is that this offer a toolbox to engineer interaction between modes and have novel devices. So let me now focus on a special kind of photonic crystal resonator we have been working on for a few years. That is actually about having many modes on the same resonator. So the idea came from the group of Dario Gerace in Pavia and Lucio Claudio Andreani. They came up with this concept from a solid-state physics that is a bichromatic confining potential. What is that? It is known that if the properties of matter are modulated with two uncommensurate periods, this creates an effective potential that results in localization of waves. So it works with matter waves in solid-state physics, but also works with photons. And this is what they have shown using photonic crystal cavities. You can notice that the big holes and the small holes here have a different period. And they demonstrate that this results into a potential for photons. As a consequence, there is a localized mode that is shown in the color map in red. Our motivation is to use this cavity to build a multimode cavity with the very tailored properties. You can understand this kind of localization effect with this analogy that is more a pattern in graphene bilayer. This is a paper of a few years ago. They show that the electronic potential is of two layers of graphene that are tilted can be engineered depending on the angle. And this is a similar effect. So let's go more in detail. This is the kind of cavity we work on. Blue holes and red and the green holes have a slightly different period. And this is actually the only control parameter we have to engineer confinement of light. And first thing is to check if this is a robust design. You may expect that if the design relies on a very simple design rule, it may be robust. So the test was to put this design in a photonic, in silicon photonic RAM that was not at all optimized for photonics. And in fact, it was a general purpose with many kind of different photonic circuit, and with no special post-processing as often required. It's just we make a photonic crystal exactly as we make any other thing. And the result is that we achieved a Q factor that is about is close to 1 million, actually 600,000, which is the largest at the time achieved in a silicon cavity made by CMOS process with no post-processing and using standard lithography. We made also statistics, so it's not just a zero result. We have about hundreds cavities, and they worked all well with a spread that is consistent with the typical fabrication tolerances. So this shows that you can actually make photonic crystal even with the standard fabrication process. But now let's go to the properties of these cavities when you let the modes interact. So the first remark is that this kind of photonic potential that I mentioned, we actually noticed that is equivalent of parabolic potential. First remark, it was demonstrated that in a photonic crystal, photons near the band gap of the photonic crystal are described by a Schrödinger equation. So Schrödinger equation is described by the effective mass of the particles, here the photons, is omega kk, and the potential. If this potential is parabolic, what you have is a quantum mechanical harmonic oscillator. And what is the property of the harmonic oscillator is that the modes are all equispaced. So this is interesting because, as you will see in a moment, I just want to mention that there are other ways to demonstrate a photonic, parabolic photonic potential, for instance, in this kind of bottle resonator that are made by tapering a fiber. So the modes are the whispering gallery modes that are circulating around this fiber. So this is the calculation on the left-hand side. What you see is the envelopes of 8 modes that exist in the cavity that I've shown you before, in photonic crystal cavity. And they do look like the Gauss-Hermite mode that you have in a harmonic oscillator. And more importantly, they are equispaced. This works not only in theory, this was verified experimentally, and what you have on the right-hand side is the spectrum of linear scattering spectrum of the optical modes, where you see the resonances there, and they are all IQ. Q factor is, in any case, about 100,000, peaking at about 600,000, and they are almost equispaced. So we performed statistics on about 300 modes, and we had a mean Q factor for the intrinsic Q factor about 700,000. But more importantly, we focused on the mismatch between the resonances. And a meaning mismatch is the deviation from a perfectly regular free spectral range. So as you can see in the statistics, we have a mean value of the mismatch that is 0, which means that in theory, if we had no fabrication tolerances, this cavity would have modes that are equally spaced. But because of disorder, this mismatch tends to fluctuate with the typical deviation that is about 50 gigahertz. So what you can do with that? Well, first, let's look at what happens if those modes are superposed. So, for instance, if you have locking of modes in a Fabry-Perot cavity, you know that you have a pulse that moves back and forth in the cavity like a particle that hits hard border and moves at constant speed. On the other hand, when you lock the Gauss-Hermite mode of this resonator, you have a pendular motion. So you would have a pulse that moves back and forth like a pendulum. So this is very different. And if you, how you can do that? So you can do that with, as I said, with our cavity. You can do that with a chirped distributed Bragg grating. And the interesting thing is that the period of motion doesn't depend on the length of the cavity, it depends on the parameter of the potential. So merely the effective mass or the potential. And this can be designed by the Bragg grating. So it's tempting to think about a laser made of this in this cavity. And so what you can think of, sorry, what is happening there? Oh, okay, doesn't want to stay, sorry. So you are, I don't know this doing there. Oh, good. Oh, there's a technical problem. Oh, I cannot show this. So let's. So what I wanted to show is that you have the equation that describes that is a Gauss-Pitayevsky equation, and this equation includes the effect of nonlinearity, that is gain saturation and absorption saturation, if you realize the cavity considering a pumped region and unpumped region. And what you see if you look at the motion of the pulse that is generated, it does, as is this color map, does have a sinusoidal oscillation in space. You can look at that more precisely in this graph. So what you see in the red plot on the right-hand side is the position of this resonator of the pulse as a function of time, and it does follow exactly the motion of the harmonic potential of coherent state. So what is that? Is the photonic equivalent coherent state that you have in a quantum mechanical oscillator. Why it is interesting? It is interesting because you don't need many modes to build this very nice peak. As you can see also in the figure, this peak is very close to the hyperbolic second. You just need less 10 modes or even less. So you can build with a very small cavity. That is the main point. So this is a route to making a nanoscale mod lock laser. We have investigated Ola, and I think I have to, I don't know what is going on. Okay, let's do this way. Okay, good. So you can, we have also considered a very more complex model where we consider the slow saturation dynamics, disorder, non-exact parabolicity of the potential, and the general result is that there is a region where this in spite of this non-ideal behavior, we still have mod locking. I will not go into detail, but this is the message. Now let me move to another interesting perspective, that is to build an optical parametric oscillator. In optical parametric oscillator, the main challenge is to have efficient interaction. To have efficient interaction, you need to have all the modes interacting resonant with modes of the cavity. Because of energy conservation, the modes, for instance, let's consider this degenerate pump configuration where you have two pump photons that annihilates and generates signal either. Because of energy conservation, this requires a cavity with three modes that are perfectly equispaced. So the free spectral range has to be strictly identical. This is not a trivial task. So in fact, this was first attempted using coupled photonic crystal cavities, and they could only achieve to have some parametric fluorescence, but the control of spacing led to made it impossible to harness the IQ factor that is possible in cavity. So this is a strong limit to efficiency. What we found out is a technique where we can compensate for residual mismatch by using a thermal effect. The key for that is that these modes are not homogeneous in space. Therefore, if we create a thermal gradient, it is possible to tune the spacing. And this is exactly what we have here. So in the figure on the right, you will see the two lines. The two lines are correspond to experimental points, and they represent the free spectral range on the right-hand side and the left-hand side. And as we tune the pump, we basically change the amount of energy that is dissipated in the cavity. This changes the temperature, the local temperature, and at some point, we have a perfect alignment. And since we have IQ modes, perfect alignment, we have all the conditions for efficient four-way mixing. And this creates an optical parametric oscillator, what you see here. So you have the spectrum as a function of the pump offset. The blue and the red maps represents the emission of the photons. That is first spontaneous, but as soon as the threshold is met, orders of magnitude increase of the signal idler, and actually we have efficient conversion of energy from the pump to the signal and idler. We have demonstrated a slope efficiency that is combining a pump and the idler is about close to 50%, and the threshold that is the lowest one was about 50 megawatt. So this is the smallest and the most and close to the lowest pump threshold parametric oscillator enabled using photonic crystal. But so just to appreciate how small it is, let us look to this figure. I'm showing on the right downside image of a silicon nitride optical parametric oscillator. And what you see in the square is the size occupied, the volume, the surface occupied by our cavities. So it is much smaller, and the orders of magnitude smaller pump power. So this is an interesting toolbox for, as you know, photonic optical parametric oscillator are very interesting for quantum physics. So as a kind of a perspective, I just want to mention this idea of using nanoscale equivalent of a neuron in photonics. So the idea was the point was raised a few years ago. So a neuron is one of the biological plausible model for a neuron is this called the leak integrated fire model. And it was pointed out that this describes the semiconductor laser with saturable absorber. And actually, there are demonstrations in physics, in photonics, of this behavior that is a spiking behavior. So here you have example, and in particular, is well known that it was demonstrated by Sylvain Barbet that VCSEL, that are very small laser, with the saturable absorber, have a behavior that is described by this Lie integrated file model. So the question is going nanoscale, so even smaller devices. So in the next talk, you will see a technology that has demonstrated many interesting properties. One of the properties that you can use a photocrystal laser to have self-pulsing, that is a related property, and this based on nonlinear resonant feedback. But the question is, can we miniaturize with a photonic crystal a spiking laser that is based on a saturable absorber, and possibly using this nanophotonic dyed laser technology? So these are preliminary theoretical results. So I want to point out that the structure is very simple. Is a kind of laser with two sections. And when the scale is about 10 micron, you have to worry about many things: diffusion of carriers, the fact that the spontaneous emission factor is very large, so you have a lot of noise. Yet the stochastic simulation that we have been carried out, is this one example, shows that you do have spiking, and you can have interesting properties. So, you can obtain the properties that are interesting for spiking, and so reproduce a photonic nerve. Yeah, so let me go to the conclusion. Well, there is one conclusion. The conclusion is, in my opinion, that you have to take photonic crystals seriously, because they can be a key enabler for nanoscale photonics. And there are a few reasons for that. CMOS fabrication is possible. They provide an ultimate confinement light in dielectrics. An example, we demonstrated as an example a microwatt scale optical parametric oscillator. And there are many new devices in perspective. And with that, I thank you for your attention.
Yeah, thanks for this very great and interesting talk. The floor is open for questions. Okay, Johann Peter Reitmeier, please.
Yes, thank you for the very nice talk, and give a nice overview about the potential of photonic crystals. I have a more general, theoretically related question. So you mentioned that you use the Schrödinger equation for calculating the mode profile and what is the eigenstates on this parabolic shaped potential. So what is is there any physical argument, or you use in principle the analogy so between Helmholtz equation and Schrödinger equation? Is there a physical argument why to use because you don't use any field quantization or anything else? So this is
no. This is a purely classical electrodynamics effect. So there is no quantum. It's just an analogy.
Okay,
so
you use the analogy between the two equations.
Exactly. So
sorry, when I want to add something, but this means you neglect then the vectoral character of the system.
Okay, this is a very important and very difficult question, because the answer is very technical. So actually, if you consider the full solution of the Maxwell equation with periodic dielectrics, and you make an approximation of this equation near the band edge, it was demonstrated by Sipe and Whipple with 10 pages of calculation that you end up with an approximate equation that is the Schrödinger equation, where A is the envelope of the Bloch mode of the photonic crystal. So it is an approximate equation, but it is pretty good, in particular for shallow grating. So, for instance, a DFB grating, this approximation works very well. But it also works for photonic crystal.
Yeah, but it only addresses a single polarization. Yeah.
Well, it works with the mode that exists in the photonic crystal. So if we target a specific band edge, this band edge relates to a block mode that has a complex polarization structure. So you can say TTM is mainly T, but the polarization structure is very complex. And this is a vector object, vector field, and the envelope of this vector field is all what we are interested in. So you are happy with the scalar envelope.
I see. Okay, thank you.
But is not trivial. So this is kind of thing you put under the carpet. And you want to talk about that because it's very complicated. But this is. But for sure, you cannot base the argument on this approximation. You have to calculate the full Maxwell equation to demonstrate that. That is what we do in the figure that follows. Okay. So this is just for giving some insight.
Okay, we have time for one more quick question, if there is any. Okay, then let me ask you something about the mode blocking in this effective parabolic potential. So in a normal Fabry-Perot cavity, in the passive cavity, you wouldn't be able to sustain a pulse. You need the interplay of dispersion and nonlinearity to create a soliton pulse, like it's done in a mode-locked laser. Here, in the parabolic, it's kind of the opposite. The passive cavity would already perform support a stable pulse, and adding dispersion and nonlinearity might actually disturb that. But you showed that it still works out. Why?
Because nonlinearity here is compensating for so for instance, if there is a non-parabolicity or structural disorder, that means that all the spacing between modes is no longer uniform. It works because I think it's very difficult to give an answer, but my intuition is that this is a property of a non-spatially uniform modes. So this means that each mode is mostly localized in a part of the laser, of the structure, and therefore it is very easy to compensate some imperfection of the one mode by just changing locally the property of the matter. And this is what happens when gain is and absorption and the related index effect are free to adjust. So this is my explanation. And it's a very general property. It's also the reason why we can achieve alignment or resonances in four-way mixing. But it's really very, very insightful question.
Okay, thanks. Then it is time to move on to the next talk, which will be given by EU from the Technical University of Denmark in Lyngby, about narrow line width semiconductor phanolasers.
Yes.
Please, the floor is yours.
Yeah. And I hope you can see the screen.
Yes, however, there is some background. There's some background. Okay, background noise is gone. Please go ahead.
Okay, yeah, thank you. So yes, my name is Yu from DTU Photonic. So today is my pleasure to give you a presentation about our recent work on narrow line width semiconductor phano laser. So to begin with, I just described the motivation of our works, which relies on chip-scale communication. As we know, for integrated photonic or optoelectronic circuits, and ultra-compact microscopic lasers are needed. A specific example is that these lasers can be used for communication between CPU cores, as the transmission loss in the optical domain is much smaller than the electronic domain. And for the lasers, and the line width is one of the most important factors. A narrow line width means a higher coherence of the lasers, and it's very important in many applications. For example, optical communication, particularly this coherent optical communication where the information is encoded in the phase of the light signals. So in this case, narrow line width of the laser means less phase fluctuations, which will lead to a higher information capacity. And also the narrow line width is important in sensors, and this can be naturally understood because a narrow line width corresponds to a high resolution of the sensor. And besides the conventional applications, there are also many new arising applications where the line width also play important roles, such as these programmable photonic integrated circuits, quantum neuromorphic computing. So in any case, for optical electronic integrations, small lasers with small line widths are very desirable. However, if we look at the progress of some lasers in the way from macroscopic to microscopic, for example, starting from the algae emitting laser to VCSEL to microdisc, photonic crystal, and plasmonic lasers, as the size of the and also mode volume of the laser becomes smaller and smaller, the line width of the laser drastically increases. And this can be also well understood by the Schoenhaus formula, which shows that if the laser line width is governed by the quantum noise, and the line width should be inversely proportional to the power and the Q factor of the laser. And since for small lasers typically suffer from low power and low Q factor, and this will lead to a broader line width. And this is a fundamental problem which severely impedes the development and applications of microscopic lasers. So in the face of these problems, we're thinking about using these so-called bound state continuum, that's termed BIC in short, this kind of physics to reduce the line width for small lasers. So BIC was first proposed by the Newman and Wigner in quantum mechanics, and it was described the state that can even surrounded by extended state can exist and localize in space. So this bizarre state can be classified into two categories. So one is BIC due to symmetry or separability. For example, you have odd mode for localized state and we're surrounded by the even mode. And then they are integral overlap with zero, so that they cannot talk to each other. And also another case is BIC can be formed by interference effect. For example, you have two fields with similar amplitudes but out of phase, and then the radiation and far field can get canceled. So in this case, a specific example is that we can have two discrete states. So these two discrete states can directly interact or indirect, for example, through a continuum state. And in this case, the Hamiltonian of the system can be written like this, and we can see that if the resonance of the two state, that is omega 1, omega 2 is more the same, and also the damping rate of the modes gamma 1, gamma 2 can be balanced by their coupling rate, that is square root of gamma 1, gamma 2. And then if we diagonalize the system, we can get the two eigenstates of the system. So one has an infinite or very large Q factor that is corresponding to so-called BIC or quasi-BIC state. Another state becomes more lossy than the original optical state. And the physics is that for the BIC state is due to the destructive interference I just talked about. And also for this lossy state is due to the construct interference between the two original states. So I should emphasize that we're mostly concentrating on the second case of the BIC here. That is due to the interference effect. So a specific example in this case is that you can realize it by two photonic crystal cavities that couple with the photonic crystal waveguide, which was proposed by Noda's group. But actually, in that works, the waveguide is end-closed. So it is not really a continuous state, but instead a set of discrete states. So, but anyway, the purpose is that we want to kind of quench the leakage of the field that was originally through the continuing state. And then, because for the leaking field, that's going out through the continuous state, it comes from two branches. So one channel is from the discrete state, another is from the continuous state. So in this case, we can use this final destructive interference to cancel the field, thus trapping the field in between these two discrete states. So here, the final resonance or final interference serves as a tool to create this interference-based DIC. And besides then we come to the eigenmodes, because I just talked about there are two eigenmodes of the system. So one is the even mode, one is odd mode, depending on the phase relationship between these two discrete states, right? So then we can try to engineer the phase of the photons that propagating between these two discrete states, so that the even mode can become the BIC state. So in this case, we can do some simplifications. We can actually fold the systems, thus transforming these two cavity systems into a one cavity system with left perfect mirrors. So then we can see that these two systems are exactly identical in physics, but these one cavity systems can greatly relax the fabrication requirements, because it does not need a fine tuning of the to match the two cavities in terms of frequency and the damping rate, which is well-known challenge in nanofabrications. So then we focus on this state, and this state can be realized by, for example, photonic crystals, as just presented by Alfredo. So there are lots of examples. So for example, if we can, first of all, we can realize this so-called phenomirror part, and by just a cavity waveguide photonic crystal systems. For example, it can be just a point defect cavity coupled with the line defect box waveguide. Actually, we have already done many works previously. And then if we move to the whole structures, that is laser structures, and we can simply realize this by blocking the left part of the waveguide with air holes. And it looks very simple, but there's something non-trivial, is that the phase of the distance between the left and right mirror has to be carefully chosen so that the phase matching can be achieved at the nano cavity resonance. Based on these schemes, we have actually demonstrated these phantom lasers based on indium phosphide photonic crystals with quantum dots as the active regions, and we achieve single mode lasing, and besides we also get cell pulsations due to the passive Q switching. So here we are thinking about using this phantom BIC laser to suppress the quantum noise of the laser. So the detailed mechanisms can be explained in two ways. So the first one is called mirror phase explanation. Another way is so-called Q factor explanation. So about the mirror phase explanation, as I just mentioned, that this phantom mirror is very narrow band, right? So if you look at the reflection spectrum, it only has a high reflection around the nano cavity resonance. And this narrow band reflection is complete by a large phase variation of the phantom mirror across the resonance. So this means that if there is an spontaneous emission, there's a phase fluctuation caused by spontaneous emission in the laser system, which causes a phase fluctuation that is delta phi here. And if you look at the FP case, and this will cause a frequency drift, which is proportional to delta phi. But for the phantom lasers, since there is a strong frequency dependence of the optical phase across the resonance, so the frequency drift is proportional to the phase change, that is the original phase fluctuation subtracted by the phase change of the mirror. And since these terms can be very large, so this means that the frequency drift of phantom laser can be made much smaller than the FP case. So this explanation is maybe not that intuitive, so then we can come to the Q factor explanation. So I just mentioned that this phase, there's large phase variation across the resonance of the lateral cavity, which means that the group velocity at the resonance is also very large, and then it will lead to a longer dwell time of the photons within the discrete mode regions. So if you look at compared to the ordinary bound state where the field is rather uniform distributed, the phantom BLC thus can have the field concentrated in the discrete mode regions. So this means that if one can place active materials, which is much lossy than passive materials, only in the continuum region, and then the composite two-factor Hall system can be much improved compared to the ordinary bound state. So based on this case, we calculate the Q factor using just standard couple-mode theory. And then we can find that it's indeed the case that if the geometrical parameters of the system can be well tuned so that the lasing wavelength is around the narrow cavity resonance, and the Q factor of the whole system, as shown by this red curve, is much higher than that of the FP case, that is the black curve here. So to realize these schemes, we also use, and then based on the Langevin approaches, we can derive the line width, which is looking like this. We can find that the ratio of the line width between the FP counterpart and the final lasers is much larger than 1 and is proportional to the Q factor of the nano cavity. So to realize the systems, we also use indium phosphide, but the key difference here is that we use this so-called barrier heterostructure technology that we have developed with Professor Preston Yuben's group, also from DTU Photonics. So this technology allows us to place active materials, which is quantum well here, deterministically in space, thus separating the active and passive regions. So this is very important here. And then we characterize the laser by bumping the light through the grating coupler on the right-hand side of the structure and measuring the scattering from top of the samples. And it is indeed that we can find that if the lasing wavelength is in tune with the nanocavity resonance, and the field can be highly localized between the left part neuron and the right final neurons, which is in accordance with the FDTT simulations. And if the lasing wavelength is slightly detuned with nanocavity resonance, and the field will leak through the grating coupler, and then there's a strong scattering at the grating coupler. Then for comparisons, we also fabricate a FP cavity, which was realized by a simple L7 nanocavity here. And these two types of lasers have similar performances in terms of threshold and output power. But as you can see that the final laser is single mode, while the FP laser is multi-mode. And due to the narrowband feature of the final mirror, which we already have observed before. And then we measure the characterize the laser coherence by measuring the line width using the homodyne technique. And the left part is the result of the final laser, and the right part is the FP laser. And you can see that by increasing the bumping powers, the line width of the lasers reduces in accordance with Charlotte-Times formula. And we can find that we can achieve the smallest line width for the final laser, that is about 6 megahertz, while the FP laser is 92 megahertz. And this result is more than 20 times smaller than previous reported smallest microscopic laser line width. And we also calculate the line width reduction factor as a function of the narrow cavity Q factor and cavity length. And our current point is somewhere here. And we can find that by decreasing the size of the lasers, actually the final BSC laser will become increasingly advantageous. And also, there are more than 3 orders of line width reduction can be expected if the cavity intrinsic Q can be further improved, for example, to 10 to 6, which seems difficult in indium phosphide platform, but is totally feasible in less loss materials such as silicon and silicon nitride. So then I would like to discuss some comparisons between our systems to other physical systems. So I think many of you may be wondering that is that the separation of active or passive regions the only condition for achieving narrow line width? So to illustrate this, and then we can compare a system with, for example, these photonic molecules, so-called PT systems. And we can find that for the final BSC system, we can have the field concentrated in the passive regions, while for the PT systems, the field is distributed in both active and passive region, the PT symmetric phase, while concentrating in the active regions, the PT broken regions. So in this case, you cannot have the field concentrated in the passive regions, thus you have very limited line width reduction effect. And also we can compare a system to this so-called Borman effect or more profile engineering. So as we show here, we can see that no matter how we engineer the motor field and the optical confinement factor that of the waveguide is unchanged. And actually the threshold of the laser is only related to the optical confinement factor of the waveguide here for the final laser, which means that our final laser can reduce the line width of laser without sacrificing the threshold. But if we do this more profile engineering, that is basically we can concentrate more field in the passive regions and leaving the antinode of the field in the active regions, and then we reduce the optic confinement factor, which increases the laser threshold. And also we can compare our system with the external cavity lasers. And in this case, maybe it's not that intuitive, but if you look at equations, we can find that the line width reduction factor of final lasers is, I just showed something like this. And for the ordinary external cavity lasers, it has very similar formula, but there's extra factor here, Y, which is typically smaller than 1. Because this system works usually typically in the weak injection scheme, which means that the reflected light back to the original cavity system should be much smaller than outgoing light. Otherwise, there will be a constructive interference occurs at the right facet, which will reduce the effective reflectivity of the laser system, thus sacrificing the laser threshold. So in this case, our final laser is typically more effective in line with reduction. And also there are some other advantages such as single mode lasing, and also as we demonstrated, can be scaled into microscopic regions, while for ordinary external cavity lasers, it's bulky and it's in microscopic regions. So in the end, I would say that since the final BIC is very general physics, and our configurations can be extended to various other platforms such as heterogeneous or hybrid integrations. So there's lots of possibilities. Yeah, so I think that's all. Thank you.
Okay, thanks for this interesting talk.
Recording stopped.
Is there perhaps one quick question before we continue?
Well, I'd like to ask one.
Yes, please.
So if I understand the reasoning correctly, I would expect that there is no advantage in increasing the size of the active region, because all what matters is the field in the passive cavity. Is correct?
I think, yes, for the final BIC schemes, so I think it's better to have most of the field concentrated in the passive regions. And this actually is feasible if the intrinsic Q of narrow cavity can be made very high. Yes. But for ordinary lasers, for example, for these FP lasers, and then there's a trade-off between the line width reduction and the threshold. So then you have to consider about the threshold will increase too much because it concentrated most of field. If it concentrated most of field in the passive regions.
Okay, thank you.
Okay, it is time to move on to the next talk, which will be given by Vinaya Krishna Yoshi from the Institute of Nanostructures and Technologies and Analytics at the University of Kassel.
Hi, am I audible?
Yes, please go ahead.
Yeah. Okay. Hi, my name is Vinay Krishna
Recording
Yoshi,
in progress.
and I'm currently doing my research at the INA, Institute of Nanostructure Technology and Analytics. Today, I'm going to show you my work on indium phosphide-based quantum dot lasers emitting at 1.3 microns. This is how I'll be going about my presentation. I will talk about the introduction and the motivation for the emphasis on 1.3 micron emitting lasers. And later, I will talk about the novel approach taken for the development of these quantum dots that emit at 1.3. And this novel quantum dot gain material was processed into a couple of pulse laser operation. The difference in the two lasers with a comparison of a similar state-of-the-art quantum dot lasers will be shown. And at the end, I will summarize my presentation. So the future of photonic chips requires the integration of optoelectronic components. Over the past decade, many theoretical studies have shown significant improvement in the semiconductor device performance by using quasi-zero dimensional or quantum dots systems. The advantage of using quantum dots as an active material over other conventional laser systems include, but are not limited to, low threshold current densities or temperature insensitive performances. And when we consider the silica fiber attenuation spectrum, 3 different wavelength regimes are usable depending on the desired transmission bands. The desired transmission bands for medium to long range data communications are centered at 1.3 microns and 1.55 microns. The indium arsenide and gallium arsenide material system is widely researched at an emission wavelength of 1.3 microns. However, an emission at 1.55 is hard to accomplish, as we see. Contrary to gallium arsenide substrates, indium phosphide and indium arsenide have a smaller lattice mismatch of around 3.2%. That enables the formation of the quantum dots, which emit at the desired telecommunication wavelength of 1.55. The indium arsenide and indium phosphide material system has been researched for this purpose and is already playing a dominant role in the long wavelength laser application. And to cover also the 1.3 micron wavelength range by this same material system of indium arsenide, indium phosphide, a strongly modified growth process has to be developed. And in this presentation, these device results and initial growth process will be showed. And to grow these 1.3 micron quantum dots, we face some challenges. And before I mention them, let's see a typical structure grown in the MB for an already established 1.55 emitting quantum dots. It contains indium aluminum gallium arsenide as barrier layers with one active region of 5 monolayer indium arsenide quantum dots. And the topmost 5 monolayer quantum dot layer is used for morphological characteristics such as the shown AFM image, through which we see high density, round and homogeneous quantum dots when we talk about homogeneous quantum dots. And when we talk about the quantum dots emitting at 1.3 microns, we need to grow smaller quantum dots. The challenges we face is that the development of these quantum dots are not possible just by changing the parameters such as the thickness of the quantum dot layer or the phi-3 ratios, or even by changing the temperature, growth temperature. So this takes us to the novel growth process introduced in our test structure. A nucleation layer was grown right before the quantum dot layer in order to increase the roughness and also to increase the nucleation points for this purpose. And by evaluation through the PL spectroscopy, we recorded that 0.4 nanometer gallium arsenide had the least line width of 32.9 millielectron volts, and it was emitting at 1.23 microns under 10 Kelvin condition. So the materials gallium arsenide and aluminum arsenide were investigated for this purpose, and gallium arsenide 0.4 angstroms, 4 angstroms gallium arsenide was the one which showed the least line width. And the AFM images of these structures are also shown, in which you can see that 0.4 nanometer gallium arsenide shows more uniformly spread out and more homogeneous quantum dots when we compare to the other AFMs, where we notice like it has some quantum dashes or conglomerates of these quantum dots. And so after achieving emission at 1.3 micron, we further investigated the impact of the quantum growth rate. And as we see that we have used a 4 angstrom gallium arsenide as a nucleation layer, and while varying the growth rates from 450, 600, 750, and 900 nanometer per hour, here we recorded a further decrease in the line width when the quantum dots were grown at 600 nanometer per hour. The full width half maxima of 24.59 millielectron volts are comparable to the line widths achieved for 1.55 emitting quantum dots. And in their respective AFM images for the quantum dots grown at 600 nanometer, we notice a better uniformity across the quantum dot layer compared to the others, as we see. Okay. And the laser design, as is shown in the PPT, is also already the laser design is implemented for the growth of 1.3 quantum dot laser and was adapted from the already existing 1.55 emitting laser. The layers of the grown laser in this figure, except for the quantum dot and the gallium arsenide nucleation layer, are all lattice matched to the indium phosphide substrate. The active region is a 6 indium arsenide quantum dot layer separated by a 20 nanometer indium aluminum gallium arsenide barrier layer. The laser structure was treated with post-growth rapid thermal annealing of around 680 degrees Celsius and later processed into 2 broad area lasers for pulse laser operation. The difference between the lasers is the increment or rather improvement in the barrier layer, as we see. So since the emission wavelength is reduced, the band gap difference between the quantum dot and the barriers is consequently also reduced, resulting in a worse carrier confinement in comparison to the 1.55 emitting lasers. Hence, we expected a worse performance, especially with regards to the temperature stability. Regardless, both laser types were grown in order to see the impact of the barrier height in a direct comparison. Therefore, in order to have a similar confinement as that of the 1.55 quantum dots, we increased the aluminum content in the barrier layer to a more optimized 35% aluminum, and to have a similar quantum dot and barrier energy height difference as that of the 1.55 quantum dots. The two lasers, namely the initial laser and the optimized laser, the laser with the optimized barrier height basically, were processed into broad area lasers of varying length with a strip width of 100 microns. The PAC characteristics and the emission spectra of the broad area lasers are plotted in the figures. The emission wavelength plotted in the figure was close to the desired wavelength of 1.3 microns, as we see, and further the PAC plots in general show decrease of the slope from short to long devices as expected, and the optimized laser also shows improvement as it is. The optimized laser also shows improvement as it has less wavelength variation with the length of the device, as we see when compared to the emission spectra of the two broad area lasers. The slopes of the PI plots for the shortest laser was calculated as 0.25 milliwatt per milliampere for the initial and 0.3 milliwatt per milliampere for the optimized. In general, the optimized laser has more light output power and operates at a lesser threshold current densities for similar lengths. These results also implies that there was a reduction in carrier escape by the improvement in the barrier height. But in order to see a better impact, we performed a temperature-dependent analysis. And an analysis of the length-dependent PI characteristics resulted in the static parameters as shown in the table. The table also shows comparison of the evaluated parameters with the two broad area lasers. We notice that there is an increase in the internal loss here, internal loss or absorption of the optimized laser, and that can be attributed to the change in the barrier layer growth condition due to higher aluminum content and therefore creating non-radiative recombination centers. In general, it gives insight on device performing better with the optimized laser design when compared to a similar state-of-the-art quantum dot laser emitting at 1.55. The threshold current density at infinite cavity length and the transparency current density are already relatively low. Furthermore, the high internal quantum efficiency of 0.8 and 0.82 was maintained, whereas the typical values of 1.55 indium phosphide devices range from 0.4 to 0.6. The internal absorption of about 11.27 and the model gain of 15.23 per centimeter per quantum dot layer are similar to the values to the literature of 1.55 emitting quantum dot lasers. The temperature-dependent analysis resulted in the operation of the initial laser up to 50 degrees Celsius from 20 degrees for the broad area laser of length 977 microns, whereas the optimized laser with broad area laser of 1018 microns operates up to 90 degrees Celsius, which is already a 40 degrees improvement in the operation range. And when we plot the variation of wavelength with temperature, we observed a 0.29 nanometer per Kelvin for the optimized broad area laser, and it shows a stable ground state transition. And the impact of the barrier layer improvement for the carrier confinement is further supported by the plotting of the threshold current densities and the external quantum efficiencies against the temperature for deducing characteristic temperatures of T0 and T1. Basically, higher the characteristic temperature values, better the temperature stability of the device. And here we have a difference of 12 Kelvin for T0 and 121 Kelvin for T1, which is about 50% improvement from the initial laser. To summarize it all, a normal growth method was implemented for the growth of these 1.3 microns indium arsenide quantum dots on indium phosphide. Gallium arsenide and aluminum arsenide were investigated for the nucleation layer, and the homogeneity of these quantum dots has also been increased by the optimization of these quantum dot growth rates with a secondary indium cell. 2 lasers were designed and implemented with this new quantum gain material and later processed into broad area lasers for pulse laser characterization. We noticed that the relatively low temperature characteristics are attributed to the decreased confinement related to the barrier height when compared to the 1.55 micron devices. And the current optimization with the increased barrier height has improved the temperature stability by increasing the carrier confinement. The temperature stability will be further analyzed by reducing the impact of self-heating with the use of ridge waveguide lasers. Furthermore, an analysis of the length-dependent pH characteristics resulted in a high modal gain of 15 per centimeter and also maintained a high internal quantum efficiency of 0.82. With that, I would like to thank the PULSE project partners and the financial support provided by the through the PULSE project. And any questions?
Okay, so thanks for the good presentation. Now we have time for some questions. Okay, so if there are no other questions, let me ask you something. Are there any other parameters of the growth process or the epitaxial structure that you think you can improve further?
In the growth processes, we can, of course, change the barrier layer condition by checking its growth temperature of the barrier layer and even the phi-3 ratios of the barrier layer, as the nucleation layer will be on the barrier layer, which will create the nucleation points for our quantum dots to grow on. So currently the barrier layer hasn't been investigated as much. So probably that would also be into consideration, taking into account that that will be the growth condition for the upper layer for the active region.
Okay, thanks. Frederick?
Just a quick question. Have you tried already to fabricate narrow reach?
Sorry, I couldn't hear you.
Have you tried already to fabricate reach lasers?
Yes, we have already fabricated ridge waveguide laser, and it already shows a large improvement. I couldn't show this in the presentation right now as it was done just this week. And yeah, so for the initial laser, we had around 50 Kelvin and 70 Kelvin for T0 and T1 values, while as for right now, we have around 241.
Okay.
So it's already a large improvement, yes.
Okay, good. Then it's time to move on to the next talk, which will be given by Sylvain Barbet from the University Paris-Saclay and the Center of Nanosciences and Nanotechnologies on time symmetric and symmetry broken pulse sequences in a spiking micropillar laser with optical delayed feedback.
Yes, thank you. So good morning, everyone. So indeed, I'm going to talk about.
Excuse me, there's a lot of noise, or maybe you can need to use a little bit the microphone.
Is it better like that?
Yes, that's great. Thanks.
Okay. Okay, so this work has been done at the C2N. It's a collaboration between the C2N, which is in fact just across the street from Télécom Paris, and the University of Auckland for the theoretical part. And most of the experimental work has been done by my PhD student, Anirudh Pami. So how do we get pulses in semiconductor photonics? So the most obvious and not very efficient way is to use the gain-loss switching, when you just send very short optical pulses or electrical pulses to your laser and to get short pulses in the end. And as we know, this is not a very good method to get nice pulses. Another method is to use a self-pulsing system, or which are also called now limit cycle oscillators. So for that, for instance, you can use a laser with saturable absorber, but the problem with this kind of method is this kind of self-pulsing systems are very sensitive to noise, and in particular, the period of oscillation is very sensitive to noise. So it leads to a lot of jitter, which are pulse-to-pulse time fluctuations. Okay, so lately there have been a lot of work on dissipative solitons, and in particular, mode locking in semiconductor lasers. So you just need for that a laser which can have several longitudinal modes and to make them in phase. So to have a frequency comb, and this way you can have ultra short pulses. So it's kind of efficient way to have short pulses. But what I'm going to focus today, it's another method which is based on a regenerative pulsing with time-delayed feedback. So this method does not need a multi-mode system. You just need an excitable system which is coupled back to itself after a delay tau. What you need is a laser which works below, in fact, the laser threshold, so it can be energy efficient. The pulse rate is fixed by the delay, so this way you reduce considerably the jitter. And the application of this kind of source can be to build fully optically controllable source of optical pulses, or also for neuromorphic computing. Okay, so the system we are using at C2N is a micropillar laser with integrated saturable absorber. So I have no time to describe fully the structure, but you have a micro cavity which embeds a gain section and a saturable absorber section, which is pumped optically and which emits at about 980 nanometers. So you have a SEM picture on the left. So the pillar itself is about 5 microns in diameter, and it's covered with a silicon nitride layer for protection and for also passivation and heat removal. So above the laser threshold, this laser can work in the limit cycle oscillation regime, as you can see here. And you can have self-pulsing whose period can be controlled by the pump. The closer you are to threshold, the longer is the repetition period. And if you are far away from the threshold, you can get faster self-pulsing. The pulses are about 200 picoseconds in that case. This laser, when operated below the laser threshold, just below, can work in the excitable regime. So excitability, suppose you set the laser in just below the laser threshold and you send a short optical perturbation to this laser. If the perturbation is small enough, you get no response, but if it's just above a certain threshold, you get a large response which is calibrated. So the output response does not scale with the input perturbation. So this is a clear signature of what is called excitable behavior. And what the system we are investigating is this micro laser in the excitable regime with an optical delay feedback. So the setup is sketched here. So you just have the micropillar laser, which is pumped by a CW pump laser at 800 nanometers. It emits at 980. The emission is fed back after a round trip tau to the laser itself, and we can observe with a fast photodetector or any equipment the dynamics out of this laser. So if you send an optical signal, here it's a short optical pulse, to this system, it can respond to an excitable pulse, which can travel back and forth into the cavity and re-excite the system again. And so in the output, you will get a train of pulses. So this train of pulses is shown here in time series representation, but you can fold the time series and do what is called pseudo-space representation, which is more convenient to figure out and to see what's going on about the pulse. And you see that the existence of a single pulse train is shown here with this trajectory in this pseudo-space representation. So the model that we used for describing this system is a slightly modified Yamada model. So the Yamada model, it's a 3 different nonlinear differential equation system consisting of an equation for the intracavity intensity capital I, the gain J, and the saturable absorption Q. For the intensity, we had a feedback term with delay. Here, the delay is tau D. The pump is A, and you have other important parameter as the saturation into the system. So the main control parameters that we have is the pump A for this system and the delay tau, which are and indeed also the feedback strength kappa, which maybe I didn't mention, but it's quite low in this system. So the external cavity we use has a very low finesse. So there are a lot of losses, in fact, in the external cavity. Okay, so this system can be operated in the short term as an optical buffer, as I'm going to show you. This means that if you excite a strain and then you send another pulse in your system, you can add another pulse train in your system, and you will have two pulses in the external cavity, which will survive for a certain amount of time. So it acts like an optical buffer memory of a priori arbitrary pulse sequences. So you can also retime some pulses. Suppose you have in the cavity two pulses which are present per round trip. If you send a well-timed perturbation here, the red circle, just before the arrival of the pulse in the cavity, you can switch off the pulse and retime somehow the pulse. You can also twist the pulse if you modulate slowly here the optical pump. Then you can modulate the position of the pulse into the cavity and twist it. Here, the delay time of the external cavity is of the order of 8 nanoseconds, and you see you can twist it with the modulated pump at 80 kilohertz over a fraction of the external cavity round trip. You can also control the pulse train duration with a single short optical pulse. And here, for instance, we send the full pulse to ignite the pulse train, and we send a second optical pulse with a lower amplitude to switch off this pulse train. And it could be switched off anywhere, in fact, we want. So we have really a full control of these pulse trains, which are produced in this regenerative pulsing system. Now, what about the long-term dynamics? Long-term dynamics, okay, so the theory predicts that you have, in fact, multi-stable harmonic pulsing regimes in this system. And this is exactly what we see in our system. So for instance, if we start with the configuration where you have two pulses which are close in the system. So here I plot the separation between the pulse, so between the two furthest away pulse and the closest pulse in red and green. And you see that this separation, after several thousands of round trips, they tend to converge. Okay, for other situations and other parameters, you have the unusual situation where you have a seemingly attractive interaction between the pulses. And the pulse, in fact, they attract, and one of the pulse, in fact, somehow disappears and collide with the other pulse. And okay, we understand this, but I don't have time to explain how it works. But this is another situation. It's quite unusual in this kind of system to have this behavior of pulse attraction. In fact, you don't really have pulse attraction or pulse repelling because of pulse-to-pulse interaction, but the interaction is mediated by the net gain in the system. And it's all the net gain dynamics that gives you whether you will have attraction or repulsion between the pulse. And this is due, in fact, to the fundamental property of excitable system, in particular, the relation between spike latency and spike amplitude in excitable system. In the experiment, indeed, if we wait a sufficient amount of time, we see that we absolutely don't have an optical buffer in the long term, which means every information that we write down in the system will converge to a harmonic pulsing regime. And for instance, here we have a 2 pulse per round trip harmonic pulsing regime, where the separation between the pulse is tau over 2, tau being the delay. And if you start with 3 pulses in the cavity, you will end up with a harmonic 3 pulse per round trip pattern, each pulse being separated by tau over 3. And this is, in fact, a marker of the repulsive interaction in the system. If you have repulsive interaction, you need to equalize the pulses in the system. And very important, all these regimes, they are coexisting. So for one parameter, you can have access to a multi-stability of harmonic pulsing regime. And how do you switch between this regime? You just send optical perturbation, you write down pulses, and you can switch between these different regimes. So this is well understood by the theoretical analysis, and we can even produce basins of attraction. We show, for instance, here all the coexisting multi-stable self-pulsing regime in our system. So here you have 6 harmonic pulsing regimes, and you can, by doing some well-timed and well-defined amplitude perturbation, switch between one regime to another regime So 1 pulse to 2 pulse, 2 pulse to 3 pulse, 3 pulse to 4 pulses. Interestingly, for a high number of pulses, you can only decrease the number of pulses with a single perturbation. Okay, now we have an unusual situation. If you consider the slow saturable absorber system, then what we see is completely different. We see that if we start with the harmonic pulsing solution with equal pulse timing between the pulses, then the final asymptotic regime will be a pulse regime where the pulses don't have the same separation. Okay. If you start with 3 pulse per regime, the same. You start for 3 pulses more or less equally spaced, and then they converge to a situation which is not a harmonic pulsing regime. So we interpret this as a temporal symmetry breaking of the pulse timings. So to see that, we can plot the pulse separation at the initial stage for 2 pulses per round trip, medium stage, and final stage. You see you have a convergence to unequal pulse timing between the pulses. The same for 3 pulses per round trip. You start with a certain configuration, and you end up a convergence to a certain pulse per round trip, which does not correspond to the initial one. In the theory, if we do a bifurcation analysis of this system, what we show here is show a bifurcation diagram of the interpulse distance versus the delay in the system. And you see the existence of, okay, it's not a pitchfork bifurcation because we have limit cycle, but it looks like the usual pitchfork bifurcation that you have for a fixed point bifurcation diagram, except here we have limit cycle. So it's a period doubling bifurcation that we have here. And you clearly see that you go from a situation where you have symmetric pulse sequences to a situation where you have non-symmetric pulse sequences. And if you start, for example, after about 1000, you make a simulation, you start with equalized pulse, harmonic pulsing, the system will converge to the symmetry broken state regime. And so you can tune the regime by tuning the delay in the system. So it's very, very convenient. If you look at the intensity of each pulse, the intensity of each pulse also has a bifurcation and has a period doubling bifurcation. It means that if you start with a harmonic pulsing regime with equalized pulse, you will end up with a symmetry broken state with unequal amplitude. And you see that, okay, at the beginning, it's slightly unequal, and then the inequality in the pulses become larger if you increase the delay in the system. So the full theoretical analysis is rather complex. Here it has been done by our collaborators. We have the full bifurcation diagram. I'm not going to go into that, but just to tell you that we have analyzed the physical origin of this symmetry broken states, and they lie into the appearance of strong resonances on the system. And very interestingly, this finding is very close to what has been found also in models of delay coupled neurons, except that these delay coupled neurons are oscillators, where in our case, oscillatory behavior is self-built-in by the delay. So we don't have oscillator at the beginning, we just have an excitable system with feedback, which gives you an oscillator. If you don't have feedback, you don't have oscillator. But it's very interesting that across fields, you have the same kind of dynamics. And all these solutions for certain parameters, time symmetric and temporally symmetry broken state, they can coexist for some parameters. And it's very interesting that they can coexist. It means you can switch between them. And it can, in fact, be interesting for several applications, in particular for attractor-based computers, with this kind of system. Okay, so my conclusion, micropillar laser with saturable absorber and delayed optical feedback can act as an optical buffer memory when you act only in the short term. In the long term, you converge to a multi-stable spiking sequence, and you can switch between them at appropriate perturbations. In the slow saturable absorber regime, you have this symmetry breaking, temporal symmetry breaking regime, which is very interesting because also you can have symmetry breaking not only with 1 degree of freedom, but with multiple degrees of freedom. So there are not so many physical systems when you can study this kind of dynamics. Interestingly, this can also have some interesting application if you want to build some sources of pulses with kind of definite pulse timing between the pulse. You can do that with this kind of system. And this has application also in neuromorphic processing, in particular associative memories. And we expect that this also dynamics is generic to any kind of excitable system with delay, so in particular in neuroscience. So I thank you for your attention.
Okay, thanks for this very interesting talk. So now we have time for maybe one question. Yes, Mr. Reitmeier.
Sorry, this was not raising the hand, sorry.
I'm sorry. Okay. Are there any other questions? Okay, I have maybe one question. You showed that there, well, you have a multi-stability between a different number of pulses. I suppose there is a limit of the maximum number of pulses you can fit into the system. Do you have an idea what the what the practical limits of that are?
Yes, that's a good point. In fact, this maximum number of pulses depends on the delay and depends also more or less on the recovery time of the carrier in the system. So if you divide the delay by the recovery time, more or less you have an idea of the maximum number of pulses you can accommodate in the external cavity. And so the more the delay, the more pulses you can get and the more states you can get. So here, because we use free space delayed optical feedback, so we are more or less restricted to, let's say, tens of nanoseconds, not so much. Mm-hmm. But if you use some other kinds of delayed optical feedback, in principle, you could have a very large multi-stability between the regimes.
Okay, thanks. It's time to move on. So the originally planned talk by Dan Lenstra on ultra-short optical pulse generation was unfortunately cancelled. So we will move on straight to the last talk of the session, which will be given by Guillermo Carpintero from the University Carlos III in Madrid, and will be on thermal crosstalk effects in monolithically integrated DBR lasers.
Okay, thank you very much. Let's see. Okay, now I'm sharing already.
We don't see it yet.
Okay, so let's see.
Yes, now we see your presentation.
Okay. Now it's in full screen, right?
We see actually split screen between two slides for some reason.
Okay. Now.
Yes, now it's a single slide and full screen. So please go ahead.
Perfect. Thank you very much. And well, thank you very much for the introduction. I'm going to present this work on behalf of my PhD student, Jessica Cesar, who couldn't be here. And I'm going to show you the work that we've been doing on investigating the thermal crosstalk between monolithically integrated components on a chip, in this case, two active components, DBR lasers. Basically, first we will show you why we are doing this work, and follow by introducing the chip that we've designed for this purpose, and show you our experimental results. Basically, we are actually working on photonic integrated circuits, and our aim for this is to develop photonic systems that are small size, weight, volume. Actually, since these chips have multiple components that can share the same peltier, advantage as well is in energy consumption reduction, and allows to put many components on a chip. And often we want to have a high density to increase the number of elements that in our chip. And this introduces, at the end, it introduces crosstalk. Of course, when you put the optical waveguides together, you get the you get the optical crosstalk. This is using directional couplers. Actually, we make components out of this. We get as well RF crosstalk between high frequency signals when we put metal layers with which we aim to create microwave waveguides. There is always an overlap. Actually, this comes from the evanescent wave of the electromagnetic waves propagating through either the optical or the RF guides. And we have also experienced the thermal crosstalk because actually we have active components which dissipate heat. And we see that this heat dissipated from one component may affect the behavior of the others. Actually, we've seen this on optical heterodyne sources. Our main goal is, our main application is integrated microwave photonics. So we use optics to generate high frequencies, and we are doing this on an integrated system. I'm showing you here quite complex. This is the most complex device that we've ever fabricated monolithically on indium phosphide. This was fabricated by 3-5 Labs in Paris, in Palaiseau, within a European project that ended a long time ago. And this was our goal here was to develop an optical heterodyne source. That means that we have 2 optical wavelengths that are spaced by an RF frequency. And when we shine both on a photodiode, we actually get an RF signal which comes from the beating of the 2 optical wavelengths. And as you can see, we fabricated 2 DFB lasers next to each other. This was, of course, to make an efficient use of the expensive indium phosphide substrate. And these 2 DFB lasers passed through SOAs, were combined on chip, and were directed to a pair of photodiodes. And actually, what we saw is we are interested in tuning the wavelength of these lasers, so we can tune the RF frequency that we generate at the output of the photodiodes. In this case, we had tuning by current, and as you can see here, we were tuning DFV2. This is one of the bottom lasers in this chip. And as we tune as we increase the current to shorten the decrease the RF frequency, basically what we saw is that we had the change of the other wavelength lasers. So we had an effect that was coming both from the current change of the refractive index, changing the system, but also a thermal effect. These are combined in this laser, but the thermal effect also affects the other laser, which is just lying next to it. This made it difficult to reach some frequency, and of course the tuning, it's a bit complicated with this effect. We were able to tune from 5 to 100 gigahertz, but we had to know our lasers before we could achieve a given frequency. More recently, in generic foundry, smart photonics, this is one of the foundries that we use, commercial foundries that we use to fabricate our chips currently. We actually fabricated a DBR laser that was coupled to a match tender modulator. This is another technique to generate RF with photonics by external modulation. And what we saw, again, for economy of the chip area, we place the DBR laser next to the match center modulator that we used to introduce the RF. And basically, you can see here a picture of the two components that were placed on a aluminum nitride substrate. And this was placed on a Peltier cooling stage. When we did our first test and measured the optical output past the match tender modulator, this is what we saw. We had this is the threshold of the DBR laser. We see the increasing of the optical power as we increase the current, but soon enough, around 60 milliamp, you can see that this is a bending. And we thought, okay, we might be reaching the saturation of the laser, but that was not the case. We pushed this further, and what we saw is that what you actually see, it's the match tender modulation, which we were not actually manipulating with. We just set the bias conditions to get the maximum light through the match tender, and what we saw is that as we turn on the laser, we have this decrease, and we actually see the sign response of the match tender modulation. We actually were able to relate this to the thermal effect of the DBR laser affecting the optical path of the match tender modulator, and that was causing this change in the optical power output. Then after these experiments, we decided, okay, we need to evaluate what is the thermal crosstalk between the devices in this platform. And this is the device that we fabricated. Actually, we placed 3 DBR lasers with a 75 micron spacing between them. This is the usual distance between the components that we use to maximize the use of the indium phosphide surface. And we actually connected the 2 extreme lasers. The lasers on the edge, we both connected with an NMI to a single output. And we included in this middle DBR, we actually had this optical output on one side, but we were not really interested in the optical performance of this component. This was just to create heat between these 2 lasers. And the first thing that we thought is, okay, let's see what is the effect of adding a deep edge area, actually a deep edge trench between these 2 of lasers. So we are aiming with this to decrease the thermal conductivity between these 2 adjacent components. And this one here was just to test without this trench and with this trench. The 3 lasers were actually the same. We just replicated the design and connected these 2. So with these 2, we were able to measure the wavelength displacement of each of these lasers as we injected current on the central one. And what we actually did for the first was to characterize the top and the bottom DBR lasers together. Well, actually, one after the other. So this was an individual operation of each of the lasers. And we actually measured the wavelength position with BOSA to have the highest resolution in the wavelength, the absolute wavelength. And we measured the optical and the electrical. And what we saw, it's okay, they are in the same range. We did the same laser. And these differences here, we probably come from optical reflections that might be coming from the NMI. And this is basically the at least we're able to know. We also measure the wavelength position, but we actually know our lasers. So from this individual characterization, we selected given bias point, and we selected 80 milliamps for these two lasers, and we measured what was the wavelength change when we started to heat up the chip through the middle DVR, this heat source. And this is what we got from both lasers, the top and the bottom. This is the one with that is separated with this deep edge trench. And what we actually saw is that by the eye, you can see that the wavelengths are evolving very similarly. And actually the wavelength range that the position is moved, each laser wavelength is moving, it's very similar. And this is the range of currents we injected into the middle DVR, this heat source, from 0 milliamps to 100 milliamps. So this was measured individually, 80 milliamps in the top laser and scanning the current through the heater source, and then the bottom DVR and scanning through the heater DVR. And the results, when we plot these results in comparison, this is the starting wavelength of the two lasers at 80 milliamps. And as we scan the current, what we see is that we have this linear increase, and both behave very similarly. Actually, the slope of this curve is practically the same. For us, this is no difference. And here we are actually plotting this with the square of the current, because actually the influence through temperature is a square of its power is the square of the current. So if we do this, and we were expecting to have this linear dependence, so we remove the square dependence of the power. And actually, we wanted to compare this with heating the lasers with the Peltier. And actually, you can see here that the two lasers also behave very similarly with changing the temperature of the stage. And the values that we've got are very similar with published data on DVR lasers. And for both, the slopes really are not significant. So we actually saw that this trench is playing no effect. Actually, from the conclusions, coming now to the conclusions, what we have seen is that thermal crosstalk in photonic integrated circuits is a serious problem, because actually it has effect on the behavior of the different components on the chip. It needs to be considered at the design stage. And what we saw is that the most immediate trick that you can play, that it's adding deep etching trends that are used for cleaving marks between chips, doesn't help very much. And actually what we have come is to think about other tricks that can be played. And actually this came from thinking about, okay, but you see, we are just analyzing 7500 micron. We thought, okay, maybe increasing the spacing would play a role. So we thought about measuring, and this is what we are currently doing, measuring the dependence of one laser over the other. So fixing one and scanning the other one. Since this we have already demonstrated that doesn't play a role, we would then double the distance. So we would see if this already diminish the effect. And actually, the other trick that we can play is that we have now this metal on the top surface, so we can use it as a thermal radiator. And this is to extract the heat in between and then create a barrier by sinking heat using metals on the top of the surface. These are the current tricks that we are analyzing in this chip. Also, the position of the chips, I would say that we have to check the position of the chips within the die. And with this, just to acknowledge the funding for this work, that it's about using photonic integrated circuits in as payloads in satellites, and that's why also heat sinking is an issue, and this is how this whole study came about. And thank you very much for your attention.
Good. Thanks for this interesting talk. Are there any questions? Yes, please, Mr. Reitmeier.
Yes, very interesting. But you, in your conclusion, you said that this trench etching has no impact, or at least not significant.
Yeah.
But the main reason is because you still have, say, a high heat conductance between the structures, so that this is by far not sufficient. So is there any idea to have a much better thermal isolation, not only the distance, because at the end, if you go to the distance, then it's going in the other direction what you want to reach in an integrated circuit. But to have a more efficient thermal isolation of devices, is this not under consideration?
Oh, yes. And actually, one of the, I'll go back to this. Basically what we are now thinking is, and I think, let me see. Okay, now you see, no, this is the previous one. Actually, there are different things that we are considering. And as I said, the first one that has come to our attention is that we can use this metal as a heatsink. And actually, what we are currently doing is to contact this this pad to the substrate, to the aluminum nitride substrate, that it's cooled by the Peltier. So we actually introduce these thermal sinks that will be at the temperature of the substrate. And this should reduce the crosstalk between these two devices, because the heat generated between them should be synced at the surface.
Sure, but this still it's always a question to quantify it, because the main area is going, say, vertical. So you have even if you have a trench of 2 micron, that's only a minor blocking. And even if you cool down a certain area, I don't know if this is enough. The question is at the end, okay, if one has to really completely redesign structures, that one has to work on also vertically thermally isolated structures. But then, of course, the request and demand on the laser and temperature sensitivity of the lasers is much higher.
Yeah.
But in this case, of course, you can then also avoid crosstalk, thermal crosstalk.
Yeah. But our problem right now is the thermal crosstalk, because it's really impacting on the behavior that we expect from each of the components. And what we are aiming to do is reduce the crosstalk between components. And that's why we are thinking about what are the structures that we can put in between the lasers to reduce this crosstalk. If the lasers then change their behavior or they increase their sensitivity, actually we are thinking that the thermal energy, it's mainly, we always thought it's mainly directed towards the substrate where we have the Peltier. And that's why we put this into aluminum nitride. So we have a high conductivity towards the Peltier. And we are aiming to reduce this resistance between the layers that connect these devices to the Peltier. Actually, one of the issues that we have to consider as well is that when we are testing these devices, we usually place the aluminum nitride on top of the copper chuck to which the Peltier is attached, but we don't use any thermal conductor because any thermal conductor will make that restoring these chips will be difficult. So that's something we have also to consider on the analysis. But I mean that when you use it, you can increase the thermal conductivity of the lasers to the sinks to reduce the sensitivity of the lasers, but the thermal crosstalk between the components on the chip is always high because they are sharing the same substrate. And this is what we want to avoid, is the thermal crosstalk. The sensitivity of each of the components, we will have to address it by increasing the conductivity towards the substrate to the sink in the Peltier. But the interaction between components is something that happens within the chip, and that's why we need to find ways to reduce the thermal, increase the thermal resistance between components.
Yep. Okay. It is high time to close this session. So let me thank all the speakers of this very interesting session again. And Frédéric, you want to say something before we continue?
So thank you, Stefan. So just to remind you that there is still one session to go on mid-infrared quantum devices starting at 2 o'clock. So we have about an hour for lunch. And so I see you at 2 o'clock for this last session of the European Semiconductor Laser Workshop. Bye-bye. See you this afternoon.
Thank you very much.
Thank you.
See you soon.
See you.